their staff and said, I'm finding it very difficult to find people to manage the facilities. I said, then don't look at it as a challenge or a problem. Why don't you just train more people? Recruit 50% more people than what you need, allow for the attrition, let the industry take the rest because we really need it. And you're in the business of actual human resource creation. And said, for the first time, probably the highest ranked Indian technical institution or Indian university, IISc, would actually be running a program almost at a diploma or a certificate level to train and send out technicians who run the utilities of a fab. But that is really the requirement, and I think that is a flexibility which is increasingly being displayed. Likewise, I think there are many ways in which all of these centers, and the key thing about this entire program, and it's called the INUP program, the key thing is that these centers where high-value equipment has been installed and high-tech training is going on are functioning as nodal centers where other tier 2, tier 3 institutions send their students, their faculty, to be trained and to work on this entire space. And that's been a very, very significant thing which happened through this. The reason I mention this is that sometimes what happens is we often don't know what kind of experiments and what are being attempted and what has worked and what has the potential to work. We need to build on all of those examples. We need to build on successes that we have had so far and actually scale it up on a level which Professor Rao Tumala has put together for us. I first met him in a different job, in a different situation, in the IIT Madras director's room. I don't recall, I don't know whether he remembers that meeting we had, but we were discussing what is it that can be done to encourage the semiconductor ecosystem in India, and at that point specifically in Tamil Nadu. But subsequently, he's worked extensively on putting together a report for the India Semiconductor Research Center. I'm aware that many of you present in the audience have also contributed significantly to that endeavor, and the idea is to actually populate centers of excellence across the IITs in the country. We can build on the experience that MeitY has funded in the past, and MeitY is committed to continue to support. And on a similar scale, I believe we need to build a research network. We need to build virtual networks of researchers and others who can contribute to this effort, contribute to the effort of actually training a large number of others as well to participate in this, what can only be called India's semiconductor revolution, literally. And this transformative effort that the government has put together. Yesterday you saw the level of commitment that this particular mission, the India Semiconductor Mission, has at the highest level in the country. You heard the Prime Minister himself promising and indicating that there would be policy stability in this area to support what needs to be done. And his whole point was on, the training, the capacity building, the human resources was something that he really underlined. That's an important segment of what the India Semiconductor Mission actually promises for what, and we have funding for that activity. We can support that activity more significantly. And and this is something which will continue into our next semiconductor mission as well. What you heard was a promise that this will get support and funding for at least another decade. So which then means that you would have a sustainable policy framework within which what the universities, what the institutes across India can actually do to support a huge push in a new and emerging area of India's industrial policy has outlined. And let me underline to you, I'm not a newbie either. Last month I completed 35 years in the civil service, so I've been around for a bit. I have not, in my 35 years of civil service, come across an industrial policy program of any government in India which actually promises a subsidy on this scale for an activity. It is unprecedented. And we civil servants are very careful guys by nature, right? So we'll never give you money until you've spent yours, normally. So which means that any policy subsidy of this nature is normally disbursed only after the project has been completed and it's in commercial production. So the private entrepreneur or the private industry puts their money down first, and after that, government steps in and says, okay, here's some money, we give it to you as a reimbursement. This is the only program where money is actually distributed on what is called a pari passu basis to industry. That is, as they spend their money, we also put in our money. Now, it's a grant, it's a subsidy, it's 50% of the cost, and you add back what the state government is paying, that's about 20 to 25% of the cost. So totally about 75% of what is being invested in the semiconductor industries is something that the government is coming up with. So we, honestly, are much more invested than anybody else, because the only return that we are going to get is the success of the program. The only return that the government is going to get on behalf of the people of this country is that the semiconductor industry got established, it is in production, it continues to produce, and India has climbed another huge step in this ladder of development. So that is the only thing that India or the government or the nation gets out of it, and that's the only reason that so much money is being put down. So that is the level of commitment that the government honestly has to the success of this program. So let me assure all the academics, representatives of industry who are here today, that this is top priority as far as government is concerned. The kind of money which has been committed for this program is unprecedented. I mean, I was part of discussions about 20 years ago, a little less than 20 years ago, when actually there was a big company from a large country which falls between the Atlantic and the Pacific Oceans, and I mean, I don't know how to give you more names, but a company for which Dr. Randeep Thakur has also worked in the past, almost established a facility in India, and it just fell apart because at that point, our policy framework was not ready for $100 million grant, right? And today, we are ready for a grant of 10 billion, right? I mean, the policy commitment has completely changed, and we are in a position to make commitments and to actually put our money where our mouth is to make sure that this happens. And what I want, or what I would request on behalf of the Government of India, from all of you who are assembled here, from both academia and industry, is please rise to the occasion. Please understand the nature of the challenge. Please understand the commitment that the government has. And please come back to us if you have any issues on this. But we will. The support that MeitY has demonstrated over the past 10 years or 12 years to the INUP program, that is, I highlighted that just to tell you that we continue to stay committed in that space. We continue to support that program because we believe that that is a critical and important program. We are building on a base. It's not something that we have started without any base, but we have to build much bigger and much larger, and that is what we'd expect would be the outcome of this workshop, which Professor Tumala has so kindly hosted for us, and so many of you have joined. And I'm sure that this is a space, and when we come back to discuss this in 5 years' time or 10 years' time, we would really be proud of what we would have achieved. I'm confident that all of you together can enable that to happen. Thank you very much for joining us this afternoon, and I look forward to the deliberations of this workshop. Thank you.
Thank you so much, sir. Well, it's always an honor listening to the visions of such a visionary leader. And now, moving forward to discuss the grand challenges and opportunities for ICCs, I would like to do the honor to invite another inspiring leader who has been helping the nation to build from the ground. Please put your hands together as I extend my warm welcome and the request to the CEO of Tata Electronics, Dr. Randeep Thakur, sir, to please join us here and share his views as well. Please put your hands together as we welcome the gentleman.
Good afternoon, everyone. It is a real pleasure to be here. I want to thank Professor Tumala to give me this opportunity to join all of you. And it is difficult for me to follow after Honorable Secretary Krishnanji. I have to say that ISM, what it has done in the last 1 year especially, with a lot of drive from Honorable Minister Ashwiniji, MeitY Secretary Krishnanji, ISM CEO, Mr. Tripathi ji. I don't think this event would have been possible to the scale it is today, and had the opportunity for all of us to participate. You know, I generally use help. I have speaker notes, and so that I just kind of say, stay within boundaries what I can express. But I'm a student at heart. And one of the learning I have is from Secretary Krishnan. Together we have been in international delegations and different forums. He never uses any notes. So I'm trying to copy it, and today is my attempt in that direction. So please bear with me if I come out incoherent, but it's part of my learning, so I appreciate it. When Professor Tumala asked me, you know, Tata is doing the fab in Dulera. We have a packaging manufacturing facility that will be in Assam. Both these projects take a lot of my time, so I usually don't get to go anywhere, and I don't think Secretary Krishnanji would like me to be anywhere other than be in Dulera or Assam to make these factories, bring them up. But I have enormous respect for teachers. Professor Tumala, I appreciate very much for what you have done for the industry and what you're doing now for India. My father was a school teacher in Himachal. My father-in-law was a professor in Canada, so whenever a community of teachers comes, it's personal to me, it's important to me. So many of the professors here who are present and who are going to really shape the future talent that we need for this industry. Let's please give them a round of applause. From my standpoint, what I see personally are that in my journey in semiconductor, I went to Kurukshetra, the NIT, and did the electronics. We were 30 students back then, and we would study from Milliman Halkias and some of those books on basic electronics. We had courses in electronics, circuit theory, some classes in line communications, digital electronics, but that's about it. But that material part was very important to me. When I read materials, components, and processes class, it helped me to build my interest. So much so, I went abroad, did my master's and PhD, primarily focusing on the materials. 40 years later, I find that material, the whole of the periodic table, is what we have engaged in the research to make today's transistors, to make today's devices. It's fascinating to see. So for us, it is the teachers, it is the institutes which will make us to focus on the fundamentals. I still believe that fundamentals have a lot of leeway to make the shape of this industry in future to go in the direction of India. It still is possible because semiconductor industry always went through inflections, and today with AI and what is needed in the new products of today, it's a big inflection. So we may sound behind by decades, but inflection may just push us to the front if we do our research and focus on the right topics of research. Secretary Krishnan, Professor Rao, the key for us at the basic level is building the nation. And the steps that ISM and the government of India has taken are towards indeed building the nation. So in that journey, the role that companies will play and the role that academia will play should be very aligned. We should focus on those research topics which can go from the ideation to commercial production. And that path is very long. So the learnings in each industry, in each section of semiconductor industry has happened. We talk about if we talk to TSMC or Intel or Samsung, these manufacturing companies, in fact, Mukesh is here, talk about IBM research, they are focusing on DTCO. DTCO is design technology co-optimization. It is a learning that we did so that design and technology disconnects can be solved. Today, we are also focusing on what is called STCO, System Technology Co-optimization, because one has to be able to talk to the other. I believe for us to be successful, we need what I call as MTCO, Manufacturing Technology Co-optimization. That space and the 12 different work streams that professor has proposed, and many of you are looking at it, that MTCO theme can really make us move faster because we will prioritize very quickly what will be worth doing and what we should just shelf away. From my standpoint, I think the learning is tied to what we do. So the second example or story I want to share with you, after I finished my PhD, I went to Micron. That was my first job. And today it so turns out that Micron is also one of the company doing packaging in India. So I would go as a process engineer. So we had a fab in Boise, Idaho, and I would go in night shift to be able to run the machines to learn the basics. And I would say from my experience, the most learning I got was by doing. Interacting with the silicon, doing the actual experiments is very, very important. What sounds on the paper is very different than when you actually are doing it, running silicon, inspecting, understanding, characterizing, looking at the e-tests, looking at what to do on integration, what steps to change, which kind of machines we need to use, whether it is a chemical vapor deposition, it is some kind of wet machining, chemical reaction, and so forth. All these things will interact, but the learning is tied to silicon. So we cannot point is, we cannot simulate our way to learning semiconductors. You have to have it by doing, not by simulating. Therefore, the step that Secretary Krishnanji talked about doing it in India and having the first fab is the right strategy for our future. Now, we will do what technology exists. We paid a lot of money to acquire the technology, 5 platforms that will be engaged. We'll start making chips. We'll run wafers. A lot of the interaction will happen. We'll do our part to make sure that from your institutes, the students can come. We can have within the clean rooms areas where they can go and do the actual learning as well. So we'll work with you. But I think the reason we must get started is that we have to learn by doing, not by simulating only. So that's point number 1. The point number 2 is these 12 work streams must make sure that we are with a roadmap. We are on an aligned roadmap. What is available and what needs to be looked at. For example, the manufacturing of 3 nanometer, 2 nanometer, most of the technical risks are retired. So what are you going to pick in those 12 work streams that's going to be useful, where we can do the jump start as a country, or we can contribute globally in an effective manner? That understanding will come from many of you in the room, professors who know it way more than I can ever fathom. But to getting it right is what is going to translate into an activity in the industry. So the point is that for us to have the academic institutes and have the government working together so that the industry can really mass produce and do it, commercialize it. Three bodies have to be in sync. Otherwise, a lot of time, we can end up spending a lot of money on the ideas and research that didn't go anywhere. I know that many of you have tremendous experience. Professor Tumala himself for decades has done enormous work on packaging. They know how to turn it into industrializing, but we are available. Tata will do its part. We will work with you on identifying those areas and how to make sure that we do not go in all different directions. The other part, briefly, semiconductor industry will always be global industry. Therefore, we will, in order for us to compete, nobody will give us any incentives that, yes, we will live with lesser products, or we will absorb more cost just because it is you. We will have to compete globally. That is easier to say, very difficult to do. So the focus in the work streams that we have around quality, or how we can enhance some of the products about the reliability, let's please do that, because that is going to play a significant role for us going forward. And the last point that is near and dear to all of the young people attending here today is about skilling. What we are doing in Tata is earn and learn. So we are giving jobs to students with the intent that they can go and work in the universities on relevant topics, but at the same time they are earning. I think that is very important to do, because given we are not in the same economic shape that some of the other countries that we compete with are, we need to encourage and also take this learning and skilling to the rural India as well. I can share with you that one of the things that Secretary Krishnan did was when we started the electronic manufacturing business in Hosur, thanks to him, we started to employ 90% of our employees are female. They come from remote areas. Every 4 months, one of those 18 to 21 year of age girls becomes a Lakshmati. We see them going to the school. We have made arrangements to do that. So I think the skilling has to be looked at the grassroots level and building the talent from all parts of India, all sectors. And therefore, the research programs should be not only with IITs or ISC. I think we should look at other great colleges within the country as well, where we can get some of these things planted. So that will be on the talent. Overall, I wish you well. We look to work with you. And I want to again thank the Government of India for so accelerating this field with the muscle they provided. I always said that industry, semiconductor industry, needs three things: technology, talent, and money. But any one of them is not enough. I think the government has given us a big shot in the arm by giving the money. I think we need to make sure we speed up technology together and also build the talent. With that, thank you very much and good luck to us.
Thank you so much, sir, for sharing your insightful thoughts with all of us. I think the gentleman needs, deserves a thunderous round of applause. Come on. Well, next, ladies and gentlemen, I would like to invite a gentleman whose ultimate aim is passing on the knowledge, and I genuinely believe somebody who is actually helping to build the nation by inspiring the younger generation, by transferring the knowledge to the next generation. Deserve a round of applause as I welcome Professor Rauthuwalla sir here on the stage to talk about Vision for India to be a global hub. He's from Emeritus Professor and an advisor to MeitY. Thank you so much, sir.
Okay, namaste, greetings. I bring greetings to you from what we call IDSPS team. I got to explain that to you because this is going to be the word from here on, in my view. I stand for, of course, India. D is the design. So basically, we are a large team of people working together to build India in 4 areas. My focus is about system. Okay, as we look back, most of the companies and academics focused on components. Okay, the value comes from integration of systems. So that's what I'm going to tell you a little bit more using my slides. But for now, though, okay, so the focus need to be in what I call integrated systems. So therefore, the team's name is Indian Design, Semiconductors, Packaging, and Systems. So most of you think of me as a packaging guy, therefore what we're doing is packaging. No. Okay, what we're doing is the entire system, not just for computing, or 6G, or IoT, okay, almost any system you can think of, okay, you could do that if you focused on 12 different technologies, create what I call industry co-development centers, that I'm going to talk about a little bit more. But for now, though, I want to take the opportunity to welcome, okay, you, all of you, okay. Clearly, for now, let me say that, okay, the Honorable Secretary Krishnan and Randir Thakur. So thank you for taking the time to come here and set the stage for what we need to do as a team in India. So before before I go with my presentation, I'd like to present to you a proposal to transform India, okay? And that's what I'm going to talk about a little bit more. For now, let me pass on 2 proposals. So may I ask you to come here? Could somebody take a photo, please? The vision is just a vision for India to be a global hub for system foundry with advanced design, semiconductor, packaging, and system technologies. I know that's a long one, but the point of all of that is, in my view, most of the companies, including TSMC, came from semiconductor roots. India, in my view, is capable of coming from system roots because the end goal is system. Okay, you might have a leapfrog and assume that role and focus on that. That's what the proposal is. May I also give you, sir, what you're going to see is the output of about 100 faculty proposing about 110 to 120 projects already in the first year. And we're requesting the ministry to fund, to fund 12 industry-centric centers to enable this vision that I'm going to describe in some detail using slides. Thank you, sir. Thank you, thank you, thank you. Can you take a photo? Yeah. So, okay, may I start with slides? Okay, I can do that. Greetings from Indian, please get used to that. Indian, DSPS, design, very important part of everything we do. Semiconductors, very important part of system is semiconductors. Packaging of those semiconductors towards a system, therefore a system. Okay, so a vision for India to be a global hub for system foundries with advances in all those areas. Okay, that's the output of the proposal that I'm going to talk briefly about. But we have faculty going into the details, okay, of all of these technologies. So those of you, most of you think of me as a professor, okay? I am, okay, I've been, but I'm also industrial technologies. I came from IBM world of, okay, advanced systems, developing technologies from concept to development to manufacturing and systems, the whole 9 yards. Okay, that's what India needs to do because that's where the money is, that's where the value is, and that's where the intellectual power needs to be. So this is the agenda we have for today. So we have 4 sessions today. First was the inaugural. I'm the last speaker in that session. Following that, we have 12 faculty leaders for 12 industry co-development centers. They don't have the time to go to a lot of details, but they will briefly give you highlights using about 4 or 5 slides in about 5 minutes. But we have a very big proposal, probably about 200-300 pages long. We'll provide at some point in time that proposal to all of you. But for now, we're going to limit that proposal only to those companies, okay, and the institutes that are participating in it for now. We don't have enough copies to distribute. So following that session by the academic professors, we'll move to a director's session. Commitment from the directors to install these centers is extremely important because they're not faculty and student centers anymore. It's industry co-development centers, very different. Okay, so unless there's a commitment from the directors of each of the institutes participating, it's unlikely they'll be successful. I'm going to talk a little bit more about that. And then following that is the industry panel session that's going to be chaired by Veerapan. Please stand up. Okay, so he's representing the industry. So let me tell you, 2 years ago, when I started to think about this whole thing, instead of this whole thing is based on Georgia Tech model, we already proved it works beautiful. To a level where the technology is developed, okay, at Georgia Tech are now going into manufacturing. From the academic institutes, technology developed, most leading edge, going into manufacturing to enable next generation of AI and computing. Okay, that's the power of this program, industry co-development centers as opposed to centers of excellence. Okay, that's what India needs to practice and leapfrog to compared to where it is today. So the industry panel session, at this point there are 70 companies interested in co-investing. I use the word co-invest, not just interested. They want to put money. All they want is, okay, our secretary, our honorable secretary to put some money from the government, and they want to multiply that, leverage that to a level where they can create this whole new industry, okay, as we look ahead. And so at this point, out of those 70 companies, about 30 companies are here, okay, and out of those 30 companies, about 20 of them actually given us a commitment to co-invest. There's a one slide from each of the companies that we're going to simply flash, have an industry spokesperson speak to that commitment. So let me move on. So the goals of this program, let me say, you're probably confused about what this thing is all about. The goals of the program we are trying to achieve is build the nation. It's a national program, not a local program. It's countrywide, involving all the top research institutions, involving all the top private colleges and universities, all working together. That list today is 27. We expect to grow that perhaps by about 30, 35 within a year or so. But right now, most of the top research institutions are already involved in this program. Okay, as we go through that. Second is build the bridge in manufacturing. So first let me congratulate ISM and MeitY, okay, for putting the first manufacturing lines happen, for making those lines happen in Gujarat and Assam. Okay, that's a fantastic achievement. I've been coming to India for 20 years, wanting to help India. I have not been successful, okay? So seeing all those manufacturing lines go for the first time in India is unbelievable, something to be very proud of. So let's give a pair of hands for making that happen. Sir, fantastic achievement of MeitY ISM for making the first production lines happen. Thank you, Randhir, for making your share. So at this point in time, you can see the first large semiconductor plant is being built by our friend here, Taco. Thank you very much for making that. So clearly, you are well on its way to be the largest semiconductor company in India. Okay, so today you're that, okay? But we'd like you to adopt this vision of system foundry, supply to everybody in the world. You're a systems company, okay, as opposed to others. So if you look at what's going on in Gujarat, Assam, those technologies are about 1985 technologies. Some of them I developed at IBM myself, like flip chip, organic laminate. Okay, I started that in 1982. So the technology going in production in 1982, 85 plus or minus. But if you look at the way the rest of the world is focusing on for their manufacturing, there are 20, 30 technologies. I'll show you a slide. So therefore, there's a gap of 4 or 5 decades between India and the advanced countries. So my question to you is, how is India going to close that gap? Okay, the only way to bridge that gap, in my view, is by exactly doing what we're doing. Okay, so I'll try to come back and keep on telling you a very important part of what we're going to do: develop technologies that are manufacturable. The focus on manufacturability. The end goal is not demonstrating the technologies, rather choose technologies that will end up, okay, being manufacturable. Therefore, they're going into manufacturing. Third one is prepare the companies for a global subsystem, initial subsystem. Okay, the focus needs to be subsystem, eventually, of course, system. So 3 goals for the program. So this is the slide, this is the gap. So you can see where India is today. Okay, greater than 28 nanometers, laminate packaging, lead frame, okay, wide bond, flip chip, and so on. So those are 1985 technologies. Okay, but if you look at where the rest of the world, I work with a lot of companies in the US, okay, those focusing on less than 3 nanometers, more like 2. Okay, glass packaging, going in manufacturing, hybrid bonding to 1 micron, not 55, 80, 100, something like that. Okay, 3D chiplets, okay, ultra high density power, integrated power modules for electric cars. So in my view, from the research point of view, we're already at 2 nanometers or less, like companies like Intel, okay, around 15 angstroms already. So in my view, we're not that far from 0, to be honest with you. Since it takes about 10 years to develop a new technology, really we should think of moving to co-packaged optics and try to think of making products with it. And of course, that then connects to quantum computing. So the world is focusing on that, India is focusing on that. Therefore, I see, okay, a big challenge, a grand challenge. Okay, so how do we close that bridge between the left and right is very important part of what we're trying to do, okay, in this proposal. So India, as you all know, this is my perspective from outside, India has everything today, okay, technologies, knowledge, lots of institutions, okay, so it doesn't have 2 things. One is manufacturing technologies, the resources, expertise. Companies like Tata, CG Power, okay, Micron, they're solving the problem. They will solve the problem, guaranteed. So I'm not worried about manufacturing, to be honest with you. The problem we need to solve is technology problem. That red, R&D infrastructure, expertise, resources. That's what this program is all about, solving that. So that's a big problem. It requires a transformation in the way the country does, in the way the government does, in the way academics do, okay, in the way industry does what it does today. So we really have to find a way for each one of them to do it differently. So in this case, government of India should invest in infrastructure for the labs, state of the art. It's also needed to set up a system to manage all of these technologies in a way, okay, somewhat privatized, like Section 8, what you call. So that's what I request the government to do. From the academics point of view, okay, it's a multi-faculty working together, electrical, mechanical, materials, chemical, on every single problem. Very hard to do, but that's what we got to do. Involve industry engineers on campus. Okay, they have to be there, otherwise technology doesn't go into companies. And then on top of that, create industry consortium at each and every center. Remember, we're talking about 12 different centers. Okay, so that's what academics need to do compared to what they typically do. And the global industry, they need to fund R&D projects. Okay, these 110 projects that we're talking about, We expect most of them to be funded, okay, as we go through in the next 6 to 12 months. Fund them. Most importantly, put an engineer on campus. If you don't put an engineer on campus, you're not going to get much. I need some water. So you need to put engineers on campus. Therefore, they'll enroll in every project. It becomes company's project, and therefore, the companies take advantage of that and think of putting that output of their project towards the product strategy. If you don't do that, okay, then you end up having to do by yourself. Okay, and the other thing, funds PhD scholars and on and on and on. So let me move on. So India can focus on components as the rest of the world does. Okay, devices, semiconductors, power devices, components, interconnections, okay, assembly and test. So we expect to focus on each one of them and more in these 12 areas, but our end goal is not those. Okay, the end goal is integration of those towards high value add, okay, higher performance, better cost, and better reliability. Then you could do what we do today. It's integration, integration, integration. That's what I call integrated systems packaging. Okay, that then leads to what I call the system foundry concepts. So I'm not going to go into the details, but integration should be the basis of what India does as opposed to simply individual technologies. So traditionally, this is what packaging is for most people. When you think of packaging, I have this chip, I got to package it. That's what we do. To me, the value of that at that level is minimal, okay? But we spent 5 decades doing that, okay? Whereas when I looked at the problem at IBM in 1970, we concluded very quickly, if you do single chip packaging on eventually on a motherboard, you will never get the performance. Therefore, I quickly moved on, okay? I invented a concept starting in 1975. It's very much like chiplet, up to 144 chips on one substrate. The chiplets today, for example, Ponte from Intel and others, they're at about 50 chips, but they are, of course, leading edge chips to the current era. But the concept of integration towards getting a better performance, better cost, better value add has been demonstrated a long time ago. I've been manufacturing that technology since 1982 till 2014 for 30 some years, applying the technology towards $10 billion a year. Okay, more than $300 billion. So fortunately, we are moving away from the left side towards the right, and that should be the focus, except the focus needs to be towards the next generation as opposed to what I was doing back in 80s. That's the 1980 module. But that requires, the point I want to make is that requires, okay, a multidisciplinary approach. Okay, you see thermal, device, design architecture, substrate, assembly, power, on and on and on. You got to bring all of them together. This is very easy to do, okay, but what we need to do is that, therefore, the need for multidisciplinary, okay, integrated centers, okay, involving, of course, not only faculty and students, but industry engineers. So I've been in this business a long, long time. This is what I learned. System architecture drives the technologies. System is not independent, design is not independent of the technologies. System design architectures drive what technologies, okay, are required to meet the performance of the system that you're planning. So then that design then leads to what technologies you need to develop by doing research. I won't go into the details, but most of the research in the academic world, okay, does not get to the next step. This is what we call valley of death. Okay, you see the actual valley. About 3% of what's done in the research in green ends up in the orange, very, very small. Okay, so that's where the world is today, in the academic world is today to a large extent, doing fantastic research, published, but most of that does not end up in products. So how do we change that? Well, that's what actually we invented at Georgia. I invented at Georgia Tech with my team. Some of them may be here. And that's what we're going to practice, okay? That's what code development center is all about, eliminating that gap. and eventually, of course, you go into high-volume manufacturing. So this is this is actually very appropriate for faculty and directors of each of the institutes that are here. This is what you do today on the left, okay? All the universities around the globe, including in India, you have faculty and students, okay? You have some limited labs. Some of them have more, some of them have less. What I call limited labs. You don't have a state-of-the-art. For example, in India, you don't have those. So that's what you do on the left side. In these core development centers, to solve that problem of research going to technologies, more like 50%, maybe perhaps even more, we really have to do all of this integrated at each center, which means research faculty, academic faculty, students, pilot lines, okay, collaborations with others who are experts. And okay, you need to bring that entire team together into each center, okay, and design and build prototypes, and therefore they are now ready for industry acceptance towards their products. So this is very new, very different. And therefore it's very important for the directors of the institutes, okay, to see the complexity of what India needs to do, okay, for it to be an economic engine, okay? So technology to me, the end goal is not technology to me. Technology means to an end. End is economics, okay? And this will drive that. So these are, we selected 12 areas based on my expertise and experience. If you do research in these 12 areas, starting with system design architectures in the far left, okay, and devices. Right now, our focus in this program, devices, CMOS devices, leading edge, okay, power devices, very important for India, and therefore we're going to focus on devices as well. But this device research is at global level. Global level means 2 nanometers. Obviously, we're not going to put very expensive facilities to do that, but we want to find a way to develop those technologies without having spent a lot of money, okay, in any way we can. And in time, there's a need, okay, obviously, okay, you deal with that. And then, of course, substrates, okay, optics, co-packaged optics, modeling for reliability. We know how to model very well for electrical, but we don't know very well for mechanical. Most of the fails in systems are mechanical. Okay, 6G, sensors, integrated sensors, materials for everything, IC and board assembly, power electronics, thermal management, system level electrical test. So I can't think of anything that's missing here to make a system. If you really build from ground up each of those technologies, in research, leading edge research, education of students in those things, India very quickly become a global level country, okay, in these technologies, just like others. Already, we're talking about the 12 centers, and therefore, for each center, we're talking about a faculty lead and a co-faculty lead from a different institution, okay, because we want to really tie the entire country, okay, entire country of all the research institutions focusing on these 12 areas. Okay, you can see, I don't have the time to go into the details, but you can see, okay, the faculty leads and co-leads for each of those 12 areas. Okay, we call them industry co-development centers. Okay, this is where we are today. There are top, okay, research institutes in India today. Okay, public, except BITS Pilani, okay. And then you have a lot of private universities and colleges already involved, okay? And we expect to grow that to a level where every research institute, either private or public in the country, is involved in some way, okay? It won't take long. And then we also connect the whole country. Okay, so to bring India to a global level, okay, remember, you have to bring India to a global level as quickly as possible. Nobody will fund research. No company will fund research for yesterday's technologies. They'll only fund for tomorrow's because they have a need. They already solved the problem for yesterday. So therefore, we identified, the faculty here, faculty leaders identified, who are the global experts in each of the 12 areas. We want to find a way to fund them, therefore they are involved in projects with their students here in India. And perhaps, okay, our students go, okay, your students go to US as well. I want to go into the details, but Professor Swami is here. Professor Swami, where are you? Okay, so he's expert in design, and he's also expert in 6G. Okay, so he's part of the 60 team. So he will make sure the research that's going on in 60 in India is at a global level, okay, not looking back. And that goes with all the others. We also have Vinky Sundaram. Vinky, are you here? I guess you're not some other place. Okay, all right. So let me move on. So I classify all the universities, I've been in this business a long time, into 3 types. Okay, those in the first type, India calls it everything skill development, skill development, skill development. Okay, so which is okay. Okay, so to me, the first set of universities going back 100 years ago, everywhere, okay, are students start in the classrooms. So okay, it's skill development mostly, not having done the research, but you learn from the books and you teach in the classroom. That worked very well. Okay, but the top universities have moved to become what I call top universities in the world. They're all research universities. Quite a few of them are in US. There are some in India. Selectively, all of them are doing research, but not all of them. So India needs to really assume the word not skill, but education by research. Okay, so please accept the word. Research leads to the best educated students. Okay, so that's where most of the world is today. But I want India to go to the next one. Next one is industry co-development universities. In other words, universities work with industry, having their engineers on campus, okay, and therefore the output of whatever they do at universities now directly goes into products. So it's no more technical. Okay, institutes are no longer just technical only. They are economic engines for the country. If you did that, okay, which is what we're planning to do, okay, you do the right technology that will lead to India growing to obviously the 3rd largest economy, which is what your Prime Minister wants. Okay, and so let me move on. So some of you may say, why do we need 12 centers? Why don't we do it 3 or 4? I've been asked that many, many times. You need that because if you really want to cover all those product areas like automotive, like computing and AI, 6G and so on, look at the technologies you would need. And therefore, when you put all of them together, you end up with those 12, and therefore the need for 12 industry co-development centers, okay, that's the logic behind all of that. So I won't go into details, but what the research we are proposing to do is at the top, by means of the 12 industry centers. Okay, for them to be manufacturable, you got to go to one more step. You got to take the technology demonstrated into what I call technology development for manufacturability. This is what India calls it ISRC. Okay, I'm not talking about that today. We're only focusing on the top one. Okay, but at some point in time, we've got to deal with how do we take those technologies, prepare them for manufacturing, okay? And of course, once you do that, now they're ready for manufacturing, okay? So these are the companies. I borrowed this slide actually from Vinky. Okay, these are the companies interested in funding the R&D, okay, that we're talking about. They want to co-invest in these 12 centers, almost all of them. About 30 of them are here, okay, and they're ready to invest today, okay, and we expect to grow that to 50. My own goal, if you ask me my own goal in 5 years, we can get 100 companies to co-invest with 100 faculty, each advising 4 PhDs, 4 MTechs, and therefore, you add up all of that, it will become a 1,000-person industry co-development center program. 1,000-person. We are close to 0 today. Okay, in a few years, it could become, okay, if you proceed with this thinking. Okay, this is what a good infrastructure lab looks like. So we're all used to thinking wafer fabs are extremely intensive in manufacturing with chemicals. They are, okay? That's also true in packaging and systems and components, okay? Therefore, you really want to think of how do we develop clean room facilities for this kind of research, not just for semiconductors, but for systems as well. Now, all of you, okay, every company I talk to, they always say, Rao, how many students are going to produce? Okay, we asked each of the faculty involved, and they came up with their own. We added all of them up. This is what they're proposing. We think we can educate 250 PhDs in 5 years across these 12 centers, about 500 MTech, okay, and BTech 750. We want BTech doing research, okay. And instantly, many of these faculty are interested in using that facilities to train manufacturing operators, technicians, and they think they could do about 18,000, okay, in first 5 years, doubling that 36,000. So therefore, the investment in this facility is a lot more than just research, okay. I'm coming to an end. Okay, we asked what does it cost for each center. This is the actual cost of installing a center, operating a center, okay? And if you add up all of those things, actually it's not that much, to be honest. It's about 1,000 crores to install state-of-the-art facilities across all these 12 centers. And then there's about 40, 50 crores operating cost, okay, every year across all these 12 centers. So clearly, what I heard from Secretary Krishnan say, okay, we have the money, we have a need, we're ready to go. Okay, so clearly we're going to create these proposals, okay, and submit those proposals, okay, and therefore proceed with all of this. Okay, so this is my last slide. So what will be the outcome of all of them? Remember, I started with this slide as a goal. The outcome of these investments, of these R&D, co-development centers in partnership with companies, if you ask me again, what is the outcome of all of that? We're going to build a nation. It's a national program, not individual program for each company, national program for all the companies. Okay, they can share benefit from. For the next generation of DSPS, again, designs, semiconductors, packaging, and systems, technologies, and the educated workforce by doing the research. Not skill development, educated workforce. We'll also bridge the gap between manufacturing in India versus the rest of the world, because the technologies we're aiming, we want them to be manufacturable, then we feed those technologies to extend the manufacturing lines in Gujarat and Assam. Therefore, now there is a sustainable path for India to keep on manufacturing as opposed to licensing, as Dr. Randhir talked about. So provide that path, and then prepare the companies to become global foundries at system level. I hope, Randhir, you will take on that challenge and say, I want to be the system foundry because I'm a systems company. I'm the largest already. I'm already setting up fabs. I want to be the system foundry for the world. This is my last slide. Thank you very much for listening to me.
Thank you so much, sir. Ladies and gentlemen, as you all know, as Sir has also mentioned, that now we are going to discuss about Industry Co-Development Center proposals. Well, we are more than excited to have so many amazing, brilliant professors who are present here with us, who will be presenting the proposals. All right, so put your hands together as I would like to do the honor to invite the very first professor. Well, the gentleman is going to talk about system design and architecture. Please put your hands together for Professor Binod Kumar from IIT Jammu. Ladies and gentlemen, on the stage.
So thanks very much. There was a small mistake. It is not Jammu, it is Jodhpur. Although Jammu is also present in our consortium in the other vertical. So once again, welcome to the first proposal. Is it working? It's on. Is it audible at the back?
You can use hand mic.
So as Professor Kumala says, everything starts with design. So still not. maybe I will take that. Okay, so myself, Vinod, joined with my colleague, Professor Nandita from IIIT Bangalore, and she is one of the female colleagues from this ICC, and we have a lot of interest from our industrial partners like from Intel and ST Micro, and some global like those professors are also guiding us on our projects that we are going to focus. So let me put next slide. Okay. So the first thing is where is our team? Okay. So I think yeah. Sorry. So you can see a list of faculty members from different institutes, not only IITs but from the other universities also, and a mix of different topics in which their expertise lies. Okay, from the CPU design to accelerator design. Okay, and the in-memory compute architectures as well as analysis of security and privacy. So this is our cross-section area of the so this is the cross-section area of the next generation architectures. Okay, the devices that you would see in compute sector. Okay, so it's not the traditional only multi-core or mini-core design, but instead what you have is a stacking of the high bandwidth memory HBM on the left hand side, and then you see a large number of accelerators or compute engines that are stacked together in a 3D style. So from architecture viewpoint, you need to decide what kind of core configuration you will fit in, what to target a high performance, as at the same time ensure a better energy efficiency, and then also ensure that the overall architecture is able to support a security perspective and privacy. Okay, so if I summarize the broad topics which we are targeting, so we have high bandwidth compute, power efficiency, and privacy and security. Okay. So like we target a performance range of, let us say, more than 100 tera operations per second, and multimodal workloads. So the workloads can be either text, image, audio, video, and so on. And then you have in-memory style architecture to ensure that the energy dissipation per operation is somewhere in the range of picojoules. So a very ambitious target. At the same time, ensuring that you have a privacy-preserving machine learning or deep learning, so that this kind of architectures, even if you are deployed at edge devices, they offer a highly secure environment. Okay, so this is our hub and spoke model, and you can see that we have institutes spread across the breadth and width of the country. So like myself from IIT Jodhpur, and then are different institutes in different expertise areas which are going to act as our satellite centers. Okay. So and then this is the list of industry, and the list is incomplete. So you are very much welcome to join us, and help us on our research topics with your expertise, and as well as if like we would like to use our research into your products. Okay, so this is about the primary list of projects that we have in our ICC as of now, starting from accelerator design to some sort of this scalable like the design of the network, and then interconnect design, and then the different other areas for like in-memory compute as well as the workload analysis. So I will not explain in detail. This is our workforce development plan. So you can see in the right that what is the typical numbers, also already put forward by Professor Tumala in terms of the BTech, MTech that we're targeting. List of courses are mentioned, and these are some courses which are currently missing in the present curriculum. Okay. So thank you very much. And with this, the next ICC faculty would join. Thanks.
Thank you very much, Binod. I'm sorry we don't have any time for questions. We'll give them 5 minutes to talk about, okay, using 5 slides, the entire program. So thank you, Binod. Let's move on to the next one. I'll take care of this. Okay, the next one is in I know. Okay, the next one is in CMOS power devices. So this is not a packaging research program. It's an entire system. System has devices. So we're focusing on 2 devices in India as part of this program. CMOS, remaining CMOS. Okay, our expert in the country obviously is Abhishek. Okay, Dixit from MeitY, Delhi. And so I guess you can describe that. Okay.
All right, thank you. Thank you, Professor Rao. So in this ICC proposal, my friend and colleague, Professor Nihar Mahapatra from IIT Gandhinagar, is leading the effort currently. I have been leading this effort for past 2.5 years. Now I am in, in a co-lead role in this. Primarily, we also enable this so that we can take advantage of the proximity of IIT Gandhinagar to the upcoming semiconductor facilities in the country, Dholera and Sanand and so on. Okay, so Professor Nihar is actually closer to where the front end of the line kind of action is. On the next slide, I want to talk about what are the next generation needs and technical challenges. I think many eminent speakers have spoken before me, including the Secretary of MeitY as well as Professor Tumala Rao. So they have already set up a very good background on where the country needs to go, what are the technical challenges. I would say in a one-liner that we expect anywhere between 2030 and 2032, the semiconductor market to hit $1 trillion mark globally, okay? So I will move on due to the shortage of time and focus on rather the technical content. This is a very interesting slide. I'm sorry if some of you are not able to read the small fonts. We wanted to, fit in a lot of information in one slide. But what we want to emphasize here is that this ICC or Industry Co-Development Center is not about what India needs today. It is a global center. It is about what the world needs from the CMOS devices, where the global picture is in terms of R&D. So we are, as Professor Rao already said, we are indeed talking about the next generation devices here, right? So we are not talking about 28 nanometers or, around silicon nodes. We are instead talking about where state-of-the-art research is. So what we have shown is, on the left slide, if you see, we have shown where the different technologies have been in the front end of the line in the MOSFET scaling kind of a scenario, the number of transistors scaling, the Moore's law, where it is breaking. Now, I would like to draw your attention to somewhere around 2021. You can see the red line. It is deviating very much from the existing trend around 7 nanometer, and it's really saturating going to 532. And we don't know where it will go beyond 2 nanometers. What we have instead mentioned here is, disruptive technologies such as quantum computing, which is, breaking the von Neumann kind of a, architecture of the machine, as well as we talk about neuromorphic and we talk about, DNA-based computing and all disruptive kind of computing technologies. That's where hyperscaling era is going to be. In terms of what is known currently, we have the FinFETs. From that, we went to the nanosheet transistors, to the fork sheet, to the CFETs, sequential 3D, and now we are talking about stacked 2D material. So this is the kind of outlook. And I have even shown the cross-section SEM and TEM images in the second row on the right-hand side, where you can see from prominent research groups and companies what their state-of-the-art devices look like. So in our ICC, we actually want to focus on this kind of device integration and device design for the next generation devices. So here we want to little bit show where our activity is. So we have roughly divided ourselves into 3 to 4 sub-verticals, starting with semiconductor materials, where there is work on synthesis and growth, as well as characterization. So some of my colleagues are working in that area. Then we have the integrated circuit design area, where we are working both on digital as well as AMS kind of circuits. Then we are working on semiconductor process, where we have process development as well as modeling and characterization. But it is very important that in essence, the academic community needs, a foundry, a kind of a pilot line where faculty can run process lots, where we can try to integrate our device designs, where our students can go in and work with their hands on various equipment and tools. That's the kind of manpower, trained manpower, that eventually all the companies are looking for. Okay, I'll move forward to the next slide. This is the ICC core faculty team as of now. There is faculty members from various institutes, and we are truly pan-India in that sense. We have faculty members from most of the large R&D institutions in India, as well as we have global academic collaborators, Professor Suman Datta and Professor Kaushik Roy. And there are actually many other faculty members across the globe, not just in the US, that we are working with, right? Including faculty members, for instance, from Taiwan. There are a lot of faculty members who collaborate with us. On the next slide, I am showing you where are the primary and secondary centers to the hub and spoke model. So currently we take IIT Gandhinagar as the primary center, IIT Delhi as the secondary center, and we have kind of divided on what kind of areas we want to work. At IIT Delhi, our focus currently is on quantum computing and cryo CMOS side. We are doing both the process as well as device design and chip design in this area. In fact, we have some of the startup companies in this area as well. And then we have the other centers at IIT Ropar, IIT Jodhpur, as well as IISc and IIT Kharagpur. So I think I'm reaching towards the end of my slides. These are the potential industry partners. Many of them we have had a discussion with, and we have verbal commitments to some extent. As and when the project is actually approved by MeitY and it is moved forward, we will do more in terms of making a concrete picture on this. And this is just the last slide on the education plan. So we want to actually cover the entire spectrum of the students, BTechs, MTechs, and PhDs. So, and as well as we are in fact looking at the certificate courses to train larger number of people with some hands-on training. So that's all I had. Thank you very much. And I look forward to seeing you again in such an event. Thank you very much.
Okay, next device is on power devices. Shaladri, where are you? You giving for Shaladri? Okay, come on over. So this is the integrated, I'm sorry, this is the power devices. Yeah, not integration yet. The focus is on device research. As close as you can. Sure.
Sure. Sorry? Okay. So, respected dignitaries and faculty colleagues and others, good afternoon. I'm Akshay. I'm a faculty at IIT Bhubaneswar, and I stand before you to present the proposal on establishing an industry co-development center on power devices with IIT Bhubaneswar as the lead institute. So here, I think the pointer is not bright enough to light it up. So we have some stakeholders listed here. I'm the faculty lead, and Professor P.V. Satyam from IIT Bhubaneswar, Dr. Ankush Bag from IIT Guwahati are co-leads of this ICC. Then we have Mr. Guru Talapaneni from 6M as our industry lead. Professor Anand Agarwal from Ohio State University, our global academic collaborator. And Dr. Sudhiranjan Tripathi from IMRE A-Star as our global research collaborator. And Professor Shripat Karmalkar is our advisor of this ICC. So apart from this core team, We also have few other faculty members, experts in their domains, namely Dr. Abhinav Arya from IIT Bhubaneswar, Dr. Vijay from IIT Tirupati, Arvind from IIT Palakkad, and Dr. P.K. Tyagi from Delhi Technological University, and their expertise is also listed. So we have, combinedly, we have a range of expertise varying from substrate and epi growth till device modeling, design, fabrication, characterization, and testing. So being a power devices ICC, our goals are twofold. One is to develop substrates for power devices, and then to make power devices on those substrates. So in fact, I have brought, I'll show this. Sorry. Not sure we can, maybe. Okay. I'll just describe this. It's all. So this is a silicon carbide bowl, which we are going to develop or grow in our facility at IIT Bhubaneswar, supported by our industry partner 6M. So that is the first goal that has been set. That is growing large area silicon carbide substrates, initially in 8-inch, then in 12-inch. And on these substrates, we would have silicon carbide epi layers for silicon carbide devices and GaN epi layers for GaN devices. And also, we would like to demonstrate our capability in growing electronic grade diamonds because these are excellent substrates for several power device applications. Then in terms of actual power devices, we would like to concentrate on developing next generation silicon carbide devices, having the best specs as compared to the current devices. So just for even being a power devices ICC, we would be working on various types of devices. But for demonstration, I have given two devices. One is the prior art, then the futuristic devices. I don't want to go into the technical details of that, but still one can see that there is a structural difference between them, and that structural difference allows the future device, which is a trench silicon carbide MOSFETs, to have much lower on resistance as compared to the top one. And what that means is that if you use this device in our EVs, for instance, you can drive for a longer distance. The heating is low, so the cooling requirements is much simplified. So and also it can switch faster, so the size of the bulky components can be reduced. So these are all the advantages for the futuristic device, which we look forward to developing. And for developing that, we have the range of expertise, as I mentioned, all the way from substrate and epi growth by our team to simulation and modeling, device design, device fabrication, device testing and failure analysis, and device characterization. So these are the expertise that we are combining together to develop the devices. And here are the breakup of all the projects that we are proposing in order to achieve our goal. You can see the top one is the project related to silicon carbide substrate development. Then you have modeling projects, 2 and 3 are modeling projects, 4th and 5th are design and development projects. 6th is a characterization. 6th and 7th are sixth is a characterization project. 7th and 8th are testing projects, and 9th and 10th are development of GaN and gallium oxide technology projects. So this is the hub and spoke model, where IIT Bhubaneswar is the lead institute, would be developing silicon carbide and other substrates, and also leading the efforts in silicon carbide devices. We have IIT Guwahati, pioneering in GaN and gallium oxide device fabrication, then IIT Tirupati in device modeling, Palakkad in device characterization, Delhi Technological University supporting in diamond substrate growth, and also we'll be taking help from IIT Bombay in packaging and Kharagpur in thermals. These are our industry partners, as I mentioned to you. We have received interest from few companies, of which 6M is the industry lead. They have shown significant commitment towards developing silicon carbide technology in India with the collaboration of IIT Bhubaneswar, and few other companies are also have interest, and potential partners who we look forward to having on team are also listed here. In terms of the technology workforce education programs, we have some short-term goals as well as long-term goals. Due to the interest of time, I don't want to go through everything. But just to say, we look forward to developing courses on substrate and epi growth of wide bandgap semiconductors. We already have designed and floated power semiconductor devices and technology course, which is an elective for BTech, MTech, and PhD students. And recently an MTech project was also, MTech course was designed and started recently at IIT Bhubaneswar, that is Semiconductor Technology and Chip Design program. Then we also will be developing a BE in engineering physics, of which power devices will be one of the electives. So in terms of long-term goals, we look forward to training at least 60 BTech students, 40 MTech students, and 20 PhDs, and at least, or if not more, double the number of those in the next 10 years. And we would also be providing hands-on expertise for all the BTech, MTech, PhDs, and professional development courses in designing, fabrication, characterization, and testing at IIT Bhubaneswar facility, as well as the fabs that are going to come up very soon at Bhubaneswar. With that, I think I'll close it down. Thank you so much for listening.
Thank you, Akshay. Next one is interconnecting substrate by Pradeep Dixit of IIT Bombay.
So, hello everybody. I am Pradeep Dixit from IIT Bombay, and I'm leading a team to develop the next generation of interconnecting substrate. And here is this picture of my colleagues, including the various colleagues from the different disciplines, materials, we have electrical engineering. Along with that, we have two global collaborators, one from the Florida State University and another from Georgia Tech. So our vision is basically to develop this next generation interconnecting substrate for various domains, right? So our target area is not going to be only like high performance computing, but we are also going to target about the 6G generations things. We can also target high power electronics. So depending upon the domain, the substrate could be this organic substrate with high density interconnection lines, or it could be glass substrate, or it could be next generation thermal conductive substrate. Now, if you look at this particular overall master figure here, okay, so we have decided to classify all the ongoing research activity in the various areas, including the electrical design, okay, including the processing side. So in terms of the substrate, one of the most critical goal right now is to fabricate the ultra high density interconnections in case of substrate lines, okay, and to do this thing on a large area panel. So these are the two major goals, especially from the processing point of view, okay. Then we are also proposing to fabricate these kind of power components, passive components within the substrate itself, okay. And then the challenge is going to be to address about the thin substrate processing and how to handle of the various kind of aspect in that particular way. So in order to do this is some of the list of the projects which we are proposing in this particular thing. And if you look at this particular list, okay, we are addressing all those challenges which I have highlighted in the previous picture here, okay. So compared to like other SRAs, okay, so we also have this particular thing where IIT Bombay is the principal center for this particular substrate, and we are going to get this co-lead support from IIT Jodhpur. And this particular substrate being a important fundamental SRA, it is also going to support the other areas, including the thermal one, okay, including the materials at IRC and other process one, okay. These are some of the companies which are interested in that. So the company includes not only the supply chain companies, including the, let's say, materials, let's say Corning or Asahi Glass, but also the companies which are dealing with the chemical suppliers, including MKS, including the McDermott Alpha and other parts. And also we have a very strong support from Western Digital, which is going to support, is also our industrial partner here in this particular case. Okay. When we talk about the education thing, okay, we also have some theory courses, but one of the most important thing which Dr. Ranjit Thakur has mentioned, that we are going to put basically learning by doing. Okay, so at present, none of the IITs has any kind of a hands-on laboratory here. So one of the major objective of this particular SRA is to start a hands-on laboratory course where the undergraduate and postgraduate students, they can use this particular lab to learn about how to fabricate the various kind of substrate, including organic and glass substrates. Okay, I think we are done with that, and we plan to basically come out with something about 20 plus PhD student in next 5 years in this particular domain. Okay, thank you.
Okay, what Pradeep talked about is the interconnecting electronic substrate, which means electronic. Now we're moving into photonic because I see that with the next generation of high-performance computing before we go to quantum. Therefore, we got to bring that as quickly as we can. So for now, okay, Naresh from MeitY Hyderabad is going to talk about co-packaged optics research.
Mixed Tech. He's our industry lead. And we have Professor Ajay Jacobs from University of Southern California as a global advisor. Along with that, we have several faculty from across various IITs participating in this SRA. So if you look at the current technologies, the leading edge technologies, there are two primary challenges, the power and the bandwidth. On the top, you're seeing a graph showing you the cadence or the increasing capacity of the network switches that are used in the data centers. So we started out with about 640 gigabits per second kind of switches in 2010. Right now, the leading edge switches are operating at 51 terabits per second. And very soon, we expect it to be 100 terabits per second. So if you're talking of an energy consumption of about 10 picojoules per bit at 100 terabits per second, we're talking of 1 kilowatt of hour or more. So there's a significant amount of power that's getting consumed, especially when you go to higher bandwidths. And we'll have to tackle this problem. And the other trend, if you look at the last 30 years of the scaling, we see that the compute has increased by about 3 times every 2 years. So 3x in every 2 years. But if you look at the memory and the interconnect, a similar increase has not happened. So you see on the bottom here, the top one is the compute, which has grown very fast. But the memory and the interconnect has not grown. It has only grown by about 1.5x every 2 years. So there's an increasing gap between the two, and we'll have to address this. So these are the primary challenges that this SRA is trying to tackle. So for this, what we have to do is something like this. You have seen some similar images. We'll have to bring together the compute, the ASICs, that compute that's ASICs, the high bandwidth memories, and also the photonic and electronic engines on the same substrate. So this is the master figure that we are planning to fabricate and show this as a prototype. So for realizing this, we'll have to make innovations in a range of technologies, right from the electrical design. We are targeting something like 100 gigabits per second and 200 gigabits per second kind of speeds. So for that, there's a lot of electrical design that is required. There's a lot of challenges there. And we also have to come up with technologies, like hybrid bonding, wherein we do hybrid bonding down to pitches of 5 micron or less. Today, Professor Rao mentioned 1 micron. That's even more aggressive than what we were thinking. So we need to make a lot of innovations in this hybrid bonding. And hybrid bonding between silicon and silicon dyes, and indium phosphide and silicon, and so on. So there's a lot of technical challenges that need to be addressed. We also have to do the electrical and the mechanical design of the glass interposers, which will be needed to put all of these chips together. So for that, we will work with the substrate SRA from IIT Bombay. And we also need to develop this leading edge bonding techniques to do the thermocompression bonding of the HBM and the ASICs and so on. So all of this is required. A major additional thing that is required is connecting the fiber to the package. So right now we're not doing that. So how do we do this alignment of a fiber to the package and design for it and so on? So all of these challenges are going to be addressed by this SRA. So that's the plan. And how do we do this? Sorry, this is not moving. Can I move it some other way? Sorry, this is not moving. Sorry? Oh, point over here? I'm sorry, yeah, this is not working. Anyway, so the proposed approach is essentially to first make these dies. So for example, SRAM and the ASIC, we try to bond it with a hybrid bonding approach. We also have to do a hybrid bonding of the EIC and the PIC. So, and design and prepare this glass substrate. So those will be the first step, and then put all of it together on an organic substrate using the C2 bonds and so on. I'm sorry about this, yeah. While we wait for the slides, one of the Can we quickly go to the, we are already ahead of it? Back, okay, yeah, sorry, this is already further down. I mean, it's not responding, I'm clicking it very fast. So we need to improve the performance of these devices. All right, anyway, so we have a similar hub and spoke model for this SRA as you have seen with other SRAs. IIT Hyderabad will be the node, and we have a secondary node at IIT Madras. And together we'll work with IIT Bombay for the substrate. We'll work with IIC for the materials. We'll work with Kanpur for the assembly. So that's the hub and spoke model we are envisioning for this. Yeah, so this is where, yeah. So this is the hub and spoke model that we're talking of. And we also need a significant amount of work on the thermal design because we're going to dissipate a lot of heat. So all of this have to come together to make this SRE successful. We have several industry partners that have expressed interest. We are talking to Mixtech, Keynes, Lightspeed Photonics, and ANSYS. So ANSYS is helping us with some of the simulation aspects. And several potential industry partners are like Intel, Corning, TI, and so on. So this is the plan. And this is the education workforce development plan. What we are targeting is about 15 PhD students in the first 5 years, and then 30 by the end of 10 years, and similar numbers for MTech and BTech and so on. At IIT Hyderabad, we already have an MTech program in packaging. We plan to expand that and actually make it more accessible. So some of the courses that we're thinking of at various levels are shown here. So this is the plan that we have for co-packaged optics SRE. Thank you so much for your attention.
Thank you. Okay, next one is predictive modeling for mechanical reliability. Tarun Agarwal from, where are you from? IIT Gandhinagar.
Okay. Good afternoon, everyone. So for predictive modeling and co-design, the team, so I'm leading the efforts as a lead for this particular SRA. And Professor Somnath is the co-lead. So I'm from electrical, he's from mechanical. That's how we gel well. And then we have industry lead also from thermomechanical and electrical backgrounds from ANSYS and Intel. And our global academic collaborators are experts in thermomechanical reliability. So that is also, they have been advising us on this SRA. The faculty team is also very multidisciplinary in the sense that there are people from electrical, mechanical, material science with different expertise in either thermomechanical or let's say AI for reliability and or growth of the materials or characterization, microstructure characterization. And then we have cross SRA faculty because the primary objective of this SRA is to, let's say, solve the problems of other SRAs, right? So they are coming up with the prototype or what they are planning to make, and then we predict what the reliability challenges with those structures are. So as I said, the two applications which we are focusing on is the next generation high performance computing and the power modules. The 5 verticals which we divide this SRA in. So one is the electrical, electrothermal, electromechanical challenges, which there are problems related to the chip package core design. So me and Professor Anand in that. And then there are thermomechanical challenges, which Professor Ravi and Dhananjay takes care of that. There is also an interest in creating multi-physics solutions, so integrating, coupling different physics, let's say chemical with electro and thermal. So that's where that is one of the focus area. Then we have also, as we see that the predictive models need a lot of data to basically make it predictive, right? So that's where the material characterization part becomes very important, and then we have the focus area for that, and also the AI for reliability. And so you see the projects are also in these 5 verticals. So if you see the chip package core design, the problems are defined in a way that they are looking at the system level performance impact of, let's say, stress from TSVs, or looking at the different novel interconnects, and then how would the electrothermal performance of those interconnects would be. Then there is from multi-physics FEM, predicting thermomechanical reliability, developing the simulator, or let's say the mathematics of the thermomechanical reliability for thin films. So some of the projects are mentioned, and the material and interface characterization, and the AI-assisted reliability. So that's the 5 verticals, and we have projects, some of the projects in those verticals. And as we are setting up in a hub and spoke model, you see IIT GN focuses on some part of the effort where the material and interface characterization, such as microstructure and some of the reliability assessment, would be at IIT Gandhinagar, along with IIT Kharagpur focusing on AI and AI-assisted solution, IIT Roorkee looking at the system level modeling, IIT Kanpur with Nilesh for material characterization, and IIT Ropar for AI for reliability, and the FCRIT for failure mode, so mostly the shock and vibration testing, and BITS for finite element FEM simulations. So that's how different IITs or institutes come together for this SRA. And there are different industry partners which we have already talked to. ANSYS has been very involved, I think, from the start itself. And we've been talking to also Intel, and Micron has also shown interest. So there are potential future industry which we have not reached, but that's what we would like them to also talk to us and help us identify if these problems are falling in the 5 verticals, or we have to create another vertical. The education plan is very similar. We start with some numbers, BTech program, as I said. So you see one thing, you see that the number is not double, the BTech 40 to 80. It's because the BTech takes 4 years to graduate, but after that it's a pipeline, right? So it's like 40, 40, 40 every year. So then in 10 years there would be 200 with that calculation, not the double. So, but the thing is, and the MTech is graduating every 2 years. The main, if we see the workforce, which you will also see, the PDC or this certification courses are going to be a game changer, where you put a course online, and this is for industry engineer. So you can educate a wider, or let's say larger set of people using these certification courses, which is, and developing hands-on laboratory, as Pradeep also said, which is very, very important for these programs. Unless the students get their hand dirty, this is not going to work. So that is the baseline for us. That's all I think I have. Thank you.
Okay, next topic is 6G. The focus again systems as opposed to devices. 6G integrated systems. Binod, I'm sorry, Minal from IIT Kharagpur.
Okay, so very good afternoon to all of you. So I'm representing this 6G integrated systems SRA, and with me we have Professor Siddhartha Dattagupta. He is present here. Can you please raise your hand? And also another colleague from IIT Guwahati, Professor Gagan Kumar. And we have two global collaborators, Professor Madhavan Saminathan. He is present here, fortunately, with us, and Professor Tentrich from Georgia Tech. So as the name suggests, that we are mostly concentrating on the integration, and here this is the core faculty team. It is from different IITs and also from some faculty members from non-IITs. And we will be working closely together with some cross-SRE faculty teams, and particularly we have to collect the substrate from Professor Pradeep Dixit's group, substrate group. So this is the overall cross-section of our proposal. So we'll start from this glass core substrate, which will include cavities, where we'll be integrating different chiplets in MMIC form in those cavities. And on top of that, we are going to deposit different layers of low dielectric constant material, where we'll be also fabricating the passive components like the resistor, capacitors, inductors. So we have the different teams responsible for different components and integration. We also have a plan to integrate all the beamformers and antenna arrays on the same substrate. And we are considering 3D integration, so both top side and bottom sides, and it ends with a metal base. So mostly we are concentrating on the D-band frequency range for wireless backhaul network application, but we are also open to other frequency ranges. So we start from this modeling and design, both for RFIC, MMIC, as well as for this layout plan. Since we are working at very high frequency range, so for us, parasitic compensation, then how to decrease the coupling among the lines, so signal integrity analysis, those becomes very important. So finally, embedding of D-band passive component, and also the antennas, different modules, then the heat analysis, and at the end, 6G test and characterization at high frequencies. These are the list of projects, which includes starting from antenna, then the passive circuits, then then chip and substrate integration, also co-packaged optics, and we also have a vision that since some of the passive components which are based on transmission line theory, like coupler, filters, power dividers, since their sizes are very small at this frequency, so we have a plan to include them as well in this integrated module. This is the spoke and hub model. We have different components coming from different IITs. They are taking part into this project, and finally, all the integration part and testing part, it will be done at IIT Kharagpur in the main center. So I discussed about global academic collaborators. We have also a few global advisors who helped us to shape these project goals. We also have industry advisors, and these are the list of companies. We still have to approach them who might be interested in this project. These are the planned courses at three different levels. So comprehensive courses for PhD program, master degree, and BTech degree, diploma and certificate program, and also professional development courses. So in addition to the packaging part for our 6G integrated system, since we are doing at very high frequencies, some additional requirements are on RF packaging, so basically the coupling, decoupling, parasitic effect compensation, etc. Then device to packaging at millimeter wave and terahertz frequencies. So mostly the focuses will be on these things. And this is the number of expected BTech, MTech, and PhD students, considering also the satellites contribution from our satellite center. Yeah, that's all. Thank you.
Thank you very much. Next one is the integrated sensors for IoT and other applications. It's shared between IIT Delhi and BITS Pilani. I guess, Bhaskar, you're going in the talk, huh?
Thank you, sir. Okay, so I'll be talking about our ICC on integrated sensors and MEMS. And before I start, I think I'll just like to mention, one of the things that was came up in the earlier talks is what we can do with 28 nanometers 80s technology. MEMS and sensors is one sort of area where several companies in the past several years have come from nowhere to capture a huge market share. Good example is a filter from Avago or no less, which makes your microphones. So here, of course, with the current, even with the current chips, there's lot more that can be done to get innovative products out than just going by the roadmap. So that's where the MEMS and sensors fits in. And as a country, we have a real strength in this area, and I hope we can leverage this in our ICC. Okay, so this is our team. I'm faculty at IIT Delhi. Professor Venkatesh Rao from BITS Pilani is our co-lead. And our global faculty collaborators are Professor Ravindra Dhaiya from Northeastern and Professor Sunil Bhave from Purdue University. As well, we have some partners from CMTI as well as several other institutes, as you'll see in the talk. Okay, so these are part of our ICC team. Professor Madhusudan Singh from IIT Delhi works on printed sensors and chemical sensors and displays. Professor Sanket Goel from BITS Pilani, Professor Subhoga Dasgupta from ISC, Professor Biswas and Professor Jas from KGP, and Professor Dubey and Professor Ponalagu from BITS Pilani. So we have a fairly diverse team spread across India, and of course this team will grow more and more as the program advances. Okay, so what we are proposing, so in general, these are sort of the things that MEMS is going forward now that we have a high performance piezoelectric that is available, that is CMOS compatible. There's a lot of things that are being done globally, and we would like to do some of them here, including closed loop sensors, CMOS MEMS integration. It's a huge pain point for a long time, and we would like to do this much better in new and different ways, and come out with new technologies where the performance limitations are, where so right now the performance limitation is because we need to fabricate submicron air gaps over a large 6-inch wafer. So if we can get away from that, and so these are some of the device and packaging challenges, as well as IoT is really a new area of growth, and this is more of an integration thing. You have to integrate batteries, energy harvesters, in some cases printed sensors and everything onto a stack. And the last sort of area is biomedical and variables, where this is a sort of whole new area where it's like the Wild West out there. There's so much things that can be done that we are just scratching the surface there, right? So I'm happy to discuss with industry partners more, which are more specific to the requirements. MEMS is sort of a large area. So right now, this is sort of our focus here. And so like others, I have a cross section, but in our case, I have 3 stacks instead of 1. So on the left is a conventional MEMS stack, which includes MEMS, cap wafer, and some ASIC integration. So here we are doing things at all 3 levels, new actuation principles and new sensors, new integration methods, as well as new packaging technologies for making the cap. The second is an IoT stack. So this typically has a power source, energy harvesters, printed circuits with some sort of, so this is your, goes into your smartwatch or an AirTag, this is what you're looking at. So in many cases, some of these things are extremely low cost, so you need to have integration methods also which uses some of these printed power sources and harvesters. And third is a microfluidic stack. Here one part is sort of high performance readout and the other part is a disposable chip you throw in and out. So again, this is a different sort of packaging challenge. Instead of having a die bond or a wire bond, you need to come up with new ways to package. So again, that's one of the things that you're working on. Okay, so technology workforce. One thing I'd like to emphasize at MEMS is one area where students work on fabricating actual devices. So most students are not working on just one aspect of a problem. They are working on everything from design to fabrication to testing. So as a hands-on experience, that's a great value add for something, not just for MEMS, but also for semiconductor industry in general, because these people have process integration experience and making things work with. So I think that way, as an educational tool, it's also a very, very important tool. So we have long term, we want to have large number of BTech, MTech, and PhDs. MTech, I think, is really the focus here because MTech is where the value add comes, because India has large number of BTech students, but really MTech is where you're taking somebody who's almost ready to something somebody who's 200% ready. So hands-on intervention at this stage would really be a great value add. And PhD will, of course, add high-level skills to some of these people. Okay, so this is our hub and spoke model. We actually have two proposed hubs, one for silicon and the other for non-silicon. So, and the hub for Silicon IT Delhi is also sort of co-located with the devices SRA, so lot of the equipment and space is shared in that way. Okay, so these are some of the projects that we are proposing. Professor Madhusudan Singh project on combinatorial sensing of heavy metals, my own research on internal electric construction for sensors and actuators. Then there are printed sensors by Professor Subodh Dasgupta. Professor Karbi Biswas has proposed an energy harvester for batteryless IOH applications. Professor Rao, Professor Dubey, and Professor Goyal from BITS Pilani have proposed various inertial as well as micro fluidic kind of sensors for biomedical detection. And finally, there are some projects on NEMS sensors for next generation of MEMS. So I think with that, I think, yeah, okay, thank you.
Thank you. Okay, next topic is advanced materials, both for devices and packaging, and perhaps systems. Yeah. And Bhagwati from Institute of Science, Bangalore.
Yeah. Hi, I'm Bhagwati Prasad. Our ICC is leading the next generation advanced materials for packaging and beyond CMOS and as well as the beyond CMOS devices. So my co-lead is here, Praveen Kumar. He's also from ISC Bangalore. Then we have an industry lead, Ravi Bhatkal from McDermott Alpha. And then we have another industry co-lead is Arun Chandrasekhar. And then we have a global academic collaborators, Professor Raj Pulugurtha from Florida International University. He is the expert of packaging materials. And then we have another global expert is Professor Ramamurthy Ramesh. He's in Rice University, and he is experts of beyond CMOS computing materials. Okay, so this SRA would be covering all sort of packaging materials, or this ICC would be covering all sort of packaging materials. In fact, our interest is to basically collaborate with all other centers and find their need and basically work with them and find the suitable materials for them. So we would be looking for the current materials as well as the next generation materials, which includes for the packaging for the quantum computings, packaging for the neuromorphic computings, and packaging
packaging for even the extreme environment applications, for example, high temperature, high pressure, even the space. So if you want to make electronic devices for those kind of extreme environment, how we can make a packaging materials for that. So we would be working for the current ongoing challenges, like tackling the ongoing challenges of the industry, but at the same time, you would be discovering and looking for the novel materials for the next generation packaging technology. Okay, so this is the multidisciplinary India-wise faculty team we have, and they have expertise in all these sort of materials. So if you look at our team, we have Deepak Arora. He has expertise in polymer and dielectrics and electronic packaging. Then we have Ayan Chaudhary. He has expertise in functional oxide materials. Then we have Madhusudan Singh from IIT Delhi. He has expertise in printed and solution process low-cost material synthesis. Then we have Praveen here. He has expertise in packaging materials, various kind of packaging materials in electromigration. Then there is another Praveen Ramamurthy. He has expertise in organic materials. And then we have a Chandrasekhar from IIT Kharagpur, IIT Hyderabad, sorry, is a mistake here. He has expertise in magnetic materials. And then Suresh Harthi Bose, he has expertise in polymer, electromagnetic interference shielding materials. And so besides that, also, as I told that, we would be working with many other, this ICC faculties, and they have expertise in various areas, and they would be also part of our center. So that includes the Ankush Bag, who has expertise in power devices. Then Anand Roop, he would be having also collaborating with us for thermal management materials, and Pradeep Dixit from IIT Bombay, who would be collaborating with us for substrates, and the Nilesh and Siv, they would be actually collaborating with us for developing the interconnect materials. And then also we have a Satyam and Parampalli, they would be working with us for silicon carbide power devices, and Siladri would be working with the power electronics, but also would be helping us to develop the power materials for the power electronic devices. And Niresh, as he is already presented, so he would be also looking for some optoelectronic materials that would be developing. And Abhishek Dixit has presented about the CMOS devices, so we'd be also developing the materials for them. Okay, so packaging materials, basically, if we are looking for the high-end performance packaging materials, we would be looking for the heterointegrations at the wafer as well as the panel level. For that, we would be looking for various kind of materials, and that require the novel materials as well as the novel process routes. So we would be looking for all sort of these materials in the process route. Then, as Abhishek has presented, that we would that we are looking for how to develop the materials for the next generation electronic devices. So if you look today's computational architectures, which is called the von Neumann architectures, and in this von Neumann architecture, there is something called the memory wall issue. So one of the way to solve this memory wall issue is that to find the alternative platforms, computing platforms and memory platforms. One of the way is that you develop the non-volatile memory technology. For that, you have to work on the novel material systems, for example, ferroelectric materials and spintronics materials, and also you can look for the alternative way of computing, which is basically the quantum computing platforms. And then we would be also looking for those kind of materials for all those kind of platforms. So that would need for future like applications for AI and IoT, and so for that we would be discovering several novel materials. Okay. So this is how our satellites, the primary and satellite centers would look like. So ISC would be having the main primary centers, and there will be satellite centers would be in like IIT Kanpur, IIT Kharagpur, and also this Manipal Institute of Technology. They would be the satellite centers, and there will be other spoke centers all across the India. And you can see that they all have a different expertise, so we all be working together and developing the materials for the next generation technologies. Okay. So this is our global industry partner list. Here you can see that the currently interested industry partners, and then there are many other industry partners would be also interested for the materials. As we know that the materials are the backbones of all sort of technology. Whatever you do, you always need a materials. New innovations require new materials, so definitely everyone need a materials for all these kind of technology development. Okay, so this is our education programs. There's a lot of ongoing courses are there in ISC as well as in many other institutes. So we would be using those courses, as well as we'll be floating new courses. With that, there are several education programs that we would be floating. In fact, many of them are ongoing programs. Okay, and that will, some of them can be merged together and new programs can come up with that. And then we would be actually developing a lot of skilled manpower. So this list is not complete. So besides, like we would, in 5 years, we would be like creating 75 to hundreds of the BTechs and 75 to hundreds of the MTechs and several PhDs trained in the materials and processes, which is really required for that. Besides that, we will be also having the several like professional development courses, and that will actually train more than 200 to 300 professionals. Okay, so these are the list of projects. So there are 16 projects in this ICC, and these projects cover from conventional packaging material solution to the future packaging material solutions, as well as the conventional devices and beyond CMOS computing devices. So the detail about all these projects are given in these booklets, and if you are interested, please go through that. And if you really want to work on any of these projects with us, you can contact us, and then we would be very happy to discuss this further. Maybe one slide is not enough in these projects to explain everything. Okay, so that's all. Thank you.
In case you're wondering where we are, the program, we got 4 more presentations to go, each 5 minutes, 20 minutes. So if you want to take a break, please go back and come back. So we do want to finish it by, I think we asked for a little bit of extra time, but our goal is to finish by 6. We may end up more like 6:15, 6:30. So let's go with it. Following this one in the director's session, and hopefully you're still here. And then following that is the industry. So please, those of you from industry, please stay back, and because we want to give you the proposal, because you are already working with us. This is about 300-page proposal, all the stuff you're seeing here. So all we are showing today is what I call highlights, okay? But if you really look at the entire proposal, it's very, very, very thorough. And obviously, we'd like to get comments from you. So at some point in time, as the program progresses, okay, we want to get going with those projects. By the time we add up all of those, it's about 120 or so projects to start with, which means about 120 students will start on day one, okay? And it's as simple as that. And hopefully in time, we'll keep on growing and growing. That's what happened to me at Georgia Tech. I started with 47 faculty, 47 PhDs. And 5 years later, I ended up with 300 PhD students at one time. 300 PhD students across the whole campus, all working in the center. So I won't be surprised if we end up something like that here as well. So next one is an IC and board assembly by Nilesh, and he's from IIT Kanpur.
Thank you. Thank you, Professor Rao. Okay. So this particular SRA is focusing on IC assembly, board assembly, and reliability testing. With me, I have my co-lead, Professor Shiv Govind Singh from IIT Hyderabad. Our industry leads are Dr. C.L. Gan from Micron and Dr. Ravi Bhatkal from McDermid Alpha. And then our global advisors, global collaborators are Professor Vanessa Smith from Georgia Tech, and then Professor Shubhra Bansal from Purdue University. Well, it's moving forward. So this is our team. We have, as you can see, a very multidisciplinary team from faculties, from materials to electrical to mechanical to chemical engineering, from all around India. As part of this SRA, we have some of the cross SRA faculties who are also involved here, include substrates, Professor Pradeep Dikshit, materials, Professor Bhagwati, and then predictive modeling, Professor Tarun. So just to give a very high level idea, the research focus is going to be on IC assembly that includes for computing and AI, technologies like copper-to-copper hybrid bonding for IC assembly, then dielectric materials that includes underfill mold materials, board assembly, thermomechanical reliability, electrical reliability, and then for power electronics, moving from, let's say, silver sintering to sintered copper, that includes power electronics that will be all the different faculties that we have as part of our team are going to be focusing on these different aspects of IC assembly, board assembly, and reliability. There is a bit lag. Hopefully it moves forward. Okay. So these are just some initial list of projects that different faculties are at this point proposing. The handbook, the small booklet, has all the details of these projects. These have been developed through extensive discussion with all the industry. So they are not the projects, and that I'm talking for all the different SRAs as well. So all the projects that all of us have been proposing have been developed through deep technical discussion with industry experts, so that our aim is to look at what industry wants, what is something that will go into product tomorrow. As hub and spoke model, we have our primary center located in IIT Kanpur, secondary center at IIT Hyderabad, and then some of our spokes are based in IIT Jodhpur, IIT Gandhinagar, IIT Bombay, IIT Tirupati, SRM Chennai, and IIT Kharagpur. All of these will be focused on IC assembly, board assembly, and reliability. And as you can see, our industry partners include across the board everything, including IDMs, OEMs, material suppliers, equipment suppliers, and then design simulation company like ANSYS. We have research interests from all these different companies that we have considered while developing all of these projects, and we have all the company leads who have been helping us throughout this process. I won't go into all the educational program details. It is fairly similar to all the different SRAs that talks about the courses we are going to teach, the certification part, operator technician training. What I would like to focus here is the expected workforce development. So we plan to have over next 5 years or so about 100 or so workforce that will be developed, and then over 10 years we'll have about somewhere around 300 or so, 200 to 300 people that will develop at BTech, MTech, and PhD level. This does not include any of the professional development courses that would be much larger number, and then of course operators and training programs that we can run continuously using the facility that we plan to set up. So I'll stop here. If you have any questions, please feel free to contact.
He'll be around, so you can ask him some questions offline. Okay, next one is power electronics. This is the integrated systems. Remember, the focus is integration. So we have power devices, and we have other components, we have substrates, thermal power, we already talked about all of those. So what Shiladri from IIT Bombay is going to do is integrate all of them together with the designs for the next generation of electronics for electric cars, as an example.
Thank you, Professor Rao. So yeah, I am leading this area, and I'm joined by my co-lead Apurv Yadav from IIT Roorkee. Preliminary interest we have from Tata Electronics on the system side and McDermott Alpha on the material side from the industry, and these are our global academic collaborators. So start with some general context, and power electronics is with the boom and electrification in vehicles and stuff. This is what is driving power electronics. So if you look at from a market perspective, this is going to be a huge market by 2030, about $150 billion. And as you can see in this chart, a huge part of that is, as I mentioned, through vehicle electrification. Now, while that is the commercial side of it, technically, if you look at what is the global power electronics, automotive power electronics roadmap, and here I'm specifically showing the power density or how compact traction inverters need to be by US Department of Energy roadmap. You can see that right now, today, as of today, it's about 10 to 20 kilowatts per liter, whereas in 2030s, which is about 10 years from now, that needs to be 20 times or 10 times better than that. So that is where the whole idea of adopting newer design architectures and looking at it as a systems level, systems packaging problem comes up. So this is the prior art of what is done mostly in power electronics today in this kind of electric vehicles, which are driven by this kind of so-called power modules. And some of the challenges here are you have wire bonds, you have a 2D sort of layout, so you have high inductances, thermal management is one-sided, so you are limited by the size of the heat sink, and thermomechanical reliability in harsh automotive conditions is a big concern. So some of the ways in which you can address that is by this sort of integrated futuristic 3D architectures, where you are looking at this as more of an sort of an integrated system, where you have driver ICs and decoupling capacitors integrated within the module, which cuts down all your inductances. The architecture goes from being flat 2D to three-dimensional. There are multiple advantages there. You reduce the inductances through vertical power loops, and you have double-sided heat management also. So, that's the general vision of where this field is going. The circuit side of it is well understood. Now we are approaching it more of as an integration problem at the high power level. So if you look at that cross-section again, you can identify throughout that architecture various, because it's essentially it's a system design problem. So you start with architecture, design, assembly, but all throughout the ecosystem, you need innovations starting from materials to thermal management design, to thermomechanical reliability, to what kind of substrates you want to use, what kind of high temperature gate drive ICs and high temperature capacitors can be used. So there are potential advantages with this architecture, but a lot of theoretical and technical challenges here also, which all of these need to be addressed to make this architecture feasible in the near future and attain all those advantages. So the faculty team we have sort of represents all those capabilities in all those areas. I've sort of listed the down. Also want to highlight that we have global expert collaborators who are pioneers in the fields of power packaging, heterogeneous integration, high temperature die attach, reliability, copper sintering, and things like that. They're all the futuristic technologies that you would need to migrate to that futuristic cross-section that I showed. This is the hub and spoke model, similar to, this is just a visual representation of all where those expertise would lie and how we would connect and how the interactions would happen in order to make this a reality. Just a quick summary of some of the R&D projects. If you happen to have the handout, you will have details of each one slide on each of these projects. But essentially, you have things on, you can see silicon carbide, gallium nitride design. You have problems on, research projects on heterogeneous integration, reliability, thermal management. About 7 to 8 projects, which are again have been arrived at by some sort of discussion with industry partners. And these are sort of a list of global industry partners. Some of them have already expressed interest, and some of them are marked as potentially interested. And a list of example research areas of interest, I sort of color code them in terms of OEM suppliers, material suppliers, and design. And you can see there are various interests here from the industry which exist throughout the ecosystem that I talked about. And finally, this is a very similar slide to what everybody else has been showing. I don't want to go bullet by bullet, but as Professor Pradeep mentioned, hands-on is something that is very vital for this kind of systems SRA also. So we do plan to initiate those kind of hands-on lab for students, industry professionals, diploma people, technicians, which is what we, sort of a long-term education research, education target with, for this SRA. So that's all. If you have any feedback or queries or any information on these R&D projects, you can write to me at that email address. Thank you.
Okay, thank you. I want to make one announcement about two highlights. One is the individual highlight. So our friend and colleague in here, Andrew, became a member, fellow of National Academy of Engineering in India. In US, that is the highest, in my opinion, second only to Nobel laureate. Okay, it's so prestigious. So achieving that is really the highest anyone can hope for. So here he is. So thank you. The other one I'm supposed to announce is IEEE, as you all know, is the largest professional society in the world. And we have had one chapter, mostly in Bangalore, called EPS Bangalore chapter for I don't know how long. I guess I think I inaugurated that about 15 years ago. So now, it's a new chapter is being formed here in Delhi for IEEE EPS. So little by little you can see how this technology and societies and companies spreading throughout the country. And it happened actually like that in China as well. And so I'm happy to announce that there'll be two chapters in India for IEEE. Thank you. Okay, so our next topic is thermal management. We're talking about power and power and power, including the power by Shaladri just now, ultra high power. So all of that power needs to be taken away. Okay, so how do we take that heat away is what he's going to talk about.
Thank you, Professor Rao, and thank you for also acknowledging my little recognition that I got a few days back. It's wonderful and it's a pleasure to be here and talking to this august audience. My name is Anandarup Bhattacharya. I'm coming from IIT Kharagpur, and today I will talk about the ICC on thermal design and technologies. My co-lead is Dr. Amrit Ambirajan, who is a professor of practice at IISc Bangalore. Then we have the industry leads, Arun Chandrasekhar from Intel India, Arun is here, and Shailesh Joshi from Toyota in North America. They have been very intimately involved with this project and with this proposal. And the global coordinators are my good friend Justin from Purdue University and Professor Satish Kumar from Georgia Tech. Okay. So let's look at what are the industry challenges and needs. Oops. Okay. So unlike thermal is very broad, and if you look at the two segments that we are focusing right now, one is in the computing, the other is in the automotive. Now, even within computing, if you look at the total spectrum of products, starting from a smartphone to the data center, which has a high-performance servers, the problem is that the cooling challenges as well as the bottlenecks are very different as you move from segment to segment. So is the power requirements as well. So for example, I can look at immersion cooling for data centers, but I cannot think about that for a smartphone. So every segment has its own challenges, has its own bottlenecks. For example, when you talk about smartphones and tablets, it's not the components that get hot, but it's the outer casing which I'm holding while using it. That is the bottleneck. That is what is exceeding its allowable temperatures. So that's where the focus has to be. As you move towards notebooks and desktops, there is another component that comes in, which is the user ergonomics. Of course, I can dissipate a lot of power if I have a powerful fan and run it at a higher RPM, but none of us are going to be comfortable with the noise that it creates. So therefore, the total amount of air I can move is limited by the noise of the air mover, which in turn limits the total power I can pack in the system. So therefore, it's the acoustics and the user ergonomics that becomes the constraint. Then as you go to servers and data centers, it's the TJ, the junction temperature, that becomes important. And when you go to data centers, it's also about the waste heat. What do I do with all the waste heat? Am I going to reject those hundreds of kilowatts to the ambient and contribute to global warming? So therefore, these are some of the industry trends. I need to cool servers with more than 2,000 watts per XPU. When I say XPU, it's the CPU or the GPU. And today, when you integrate them along with AI accelerators, you're easily talking about higher than 5 kilowatts per substrate. That's a humongous challenge. We are talking about low acoustic air movers. We are talking about passive cooling techniques, because in smartphones and tablets, we cannot put a fan, we cannot put a pump, we cannot have liquid cooling. It's completely passively cooled. Thermal interface materials, that's the bottleneck, that's where the heat is generated. I need to transport it out with the lowest minimum possible thermal resistance, okay? The energy utilization factor for data centers, and all of these multi-physics, these are all multi-physics, multi-scale models. We need to have the modeling techniques. If you go to automotive needs, as you can see, this is the age of electrification. And therefore, the power drives are becoming very, very important with compounds. And the whole idea here is to maximize the volumetric power density, as I'm trying to show on the bottom left-hand plot, or the bottom right-hand plot for you. Okay, so these are the challenges, and therefore, what are we going to do about it? So these are two cross-sections that I'm showing here, but again, fully being aware that for a system-level challenge like thermals, it's very difficult to represent everything in one single cross-section. So these are some of the areas that we are focusing on with some of the leads, the names of the leads who are going to drive those, both in the computing as well as in the automotive domain. Okay. This is our multidisciplinary team, very similar to what others have shown. I just want to highlight 2 points here. One is it's really pan-India. You can see not just participation from IITs and IISCs, but also Jadavpur University, SRM, MIT Manipal, BITS Pilani. So truly a pan-IIT team. And we also have, as our Honorable Secretary was saying, we also have reasonably good representation from our women faculty colleagues. The hub and spoke model, so quite a few of them, as you can see. Some of them have already carved out their niche, and they are going to be leading those areas. There are some who have joined. They're interested. They're very efficient, very accomplished thermal researchers, and slowly we are going to also find out. Eventually, each site will have their differentiating expertise. And then these are the cross ICC spokes. Definitely, thermal has to work with power electronics. Thermal has to work with substrates, materials, photonics, all of them. I've already talked about Arun and Shailesh, and then we have some other industry advisors as well from different companies. And those are our industry partners whom I have listed, present and future. Arun is already here. He's going to talk about more when he comes to represent Intel. Several projects we have, actually 12 of them right now. I'm not going to go through all of them, but again, trying to address the different cooling challenges that I talked about at the beginning, both in computing and automotive domain. And having representation projects being proposed by across IITs, IISc, as well as SRM, Manipal, everybody. The workforce development, we already have something. We have a lot more to do in terms of curriculum development, in terms of development of outreach courses, and developing trained expert workforce for the country. You have some of our predictions over there, and hopefully after 5 years or 10 years, I really hope that we would beat these targets handsomely. Thank you very much.
Thank you very much, Andrup. Again, congratulations. Okay, so what you heard so far, we'll start the system design architectures. We develop devices, we develop substrates, electronic, photonic, okay, and we assemble chips, other components, okay, and we apply all of them to a variety of applications like 6G, computing, okay, sensors, on and on and on and on. That's what you heard. So once you fabricate to the system designed architectures, the final step is electrical test. Okay, system level test, because our focus is system level, therefore you got to do system level electrical test. Most of the electrical testing is really at component level in my view, except by a few companies. So really, therefore the next topic is going to be presented by Jay from IIT Tirupati. So Jay, you're on.
Thank you, Professor. Where is that slide changer? Hi everyone, my name is Janaran. I come from IIT Tirupati, and I'll be leading. Yeah. Wait a minute. Yeah. So as all of us have, I think by now we have come to know that how this structure of the Industry Core Development Center works. We have two, lead and co-lead, and then we have industry, lead and co-lead, and then we'll be having the industry and the academic experts around the globe, right? So we have myself, Janaran, and then Satyadev from IIT Jammu, and then Naveen from Marvel, and then Kamlesh from Krivya Semicon. So as the industry co-lead, right? So here are our faculty team across India, and as Professor was mentioning that, it should include not just the IIT, also the other state level universities and the internet. So we have a NIT, and then we have a Cochin universities, which are distributed across to, attempting the different problems which comes in the systems which has been specified by the system design and architecture team. And then we have a faculty team from the cross SRH, so which means that we have a faculty team within the kind of strategic research areas, and then the other, how they are related with the other research areas, SRA or the ICC we call. And here is our detail of what we are going to do and what are the problems that we will be solving. So these are the initial problem what we could put together by 1.5 years of the effort. So we have to mail them to the faculty around the India, talk with the industries, identify their challenges, what is their need it, put them together, make it a system, and as a system, how are you going to address these problems? So this is how is our mapping, as we could able to see that so mainly that our target is that, all right, what are the things that we are going to do the little differently? So which means that as these 3D, chiplet systems, what are the new problems that are going to come, and how are we going to address? So that's the whole challenge. So we'll be looking at the two problems. One is how to test the interconnects. So which means that there are a lot of interconnects that are going to connect the chiplet together, which are going to come on top of the interposer. So how are you going to test them? And what are the newer defects that we could able to, we'll get to see. So for example, there are newer defects such as the strong and the weaker, open, and the short kind of defects, which are going to result in the delay kind of fault model. So how are you going to test on chiplet? So that's the things. And so therefore you could able to see the problem is distributed across the architecture, algorithm, and how are actually we are going to test them. Yeah, and here is our hub and spoke model. As you know how this ICC is going to work. So we have a primary center at IIT Tirupati, which will be hosting the equipments and the software tools and the different compute unit, the computational devices. And then we have the secondary hub, which is going to be hosted at the IIT Jammu. And then we have a faculty team distributed across the different, the universities and the IITs, who will be addressing the different problems, whatever I have shown. And here are the companies so far. Of course, this list is it's evolving. So whoever takes the interest, so we'll be including them, whoever interested takes. As we have been discussing about, people have interest in the research, people have interest in the manpower, people have interest in the technology. So whatever the interest the company has, we always welcome them. So we could be added into this list. So therefore, it's a truly industry academia partnership in terms of developing the system which we are talking about, right? Yeah, these are the list of problems. So we have a proposal prepared, 300-page proposal. Professor has shared with all the industry colleagues, so you can go through all those details problem. But these are the initial list. It may not be the, it may not address all the problems of the testing, but at least we have around 9 to 10 problems to start with, at least to address some of the challenges of the 3D chiplet system. And then here are the expectations that we're supposed to be producing this many number of the undergrad or the grad or the PhD. In fact, initially when we were discussing, the Professor Rao gave us to produce the 100 PhDs. So, and most of the SRA felt like, it's not so easy to get to the 100. So therefore we have, somehow 70 to 75 kind of PhDs we have targeted. right? And then the BTech, MTech, and the professional kind of things, so, right? So that's the thing. So this is going to be my last slide. And just to give you a brief that what we are going to do, if you have any questions, otherwise, kind of fire an email to both of us. Thank you very much.
Thank you so much. So with that, we come to the end of all the proposals. I believe they all were really helpful, right? Right? तो तालियों की आवाज़ कम क्यों थी? Come on, please put your hands together for the entire team for presenting it so gracefully. With that, ladies and gentlemen, we are all set to start the director's session. And who can be better than moderating this session? Please put your hands together as I invite one more time Professor Rao Tumalla here on the stage with you all to conduct the session. Louder, louder, louder. Come on, everybody.
Okay, we are entering into a different topic. Thank you very much. And this will be shorter. At one time, we counted on all the directors of all the participating IITs to be here. Many of them said they will be here, but it turns out we only have about 5 or 6. Okay, there are 2 parts to this session. One is a keynote talk. Okay, remember what we're doing here is research, leading edge research, next generation. I can't think of a person other than Professor Ram Gopal as the champion for research in India. So I invited him if he's willing to come and talk about his view of research in India yesterday, and perhaps what his view, given he sat through all of the presentations, what he thinks of what we're proposing in terms of research. So Professor Ram Gopal, let's give a pair of hands.
Load my presentation slides. So. Pardon? Yeah. Just my presentation. That's good. Yeah. Okay. So I will talk about what has been happening in India. I mean, so this activity, something similar, we had planned way back in 2006. 2005, 2006, as Secretary MeitY mentioned. The time Dr. Chidambaram was the one who contacted some of us and said, can you put together a proposal? That time it all started with IIT Bombay and IISc Bangalore. I was in IIT Bombay at that time. In fact, I spent 18 years at IIT Bombay. Then I moved to IIT Delhi. So I'll give you a glimpse of what happened in the past and what we can learn from there as we move forward. I have total of 10 minutes for doing all of this. So India, if you look at India is a large country, right? Whatever you see, number of institutions, India is #1 in the world in terms of the number of institutions, and second in terms of the enrolled students in higher educational institutions. I mean, we have like 43 million students in the higher educational institutions. We are third in the world for research output now, 6th for patents, 9th for citations, but that is where all the good things stop. I think when it comes to innovation, or when it comes to India investing money in research, or in terms of academia industry collaborations, or even in terms of number of researchers per million population, we still have a long way to go, right? I mean, India is not spending enough money. We are hoping that as part of the ISM, there will be funds provided to academia for taking up the research, and that is where Professor Tumalla Rao and all of us are hoping the ISM to do, and I hope that will happen. And India is also one of the fastest growing countries in terms of research. As against the world average of 4%, we are growing at 11%. But the biggest challenge with India is the Indian industry not spending enough money on research, right? So this is Indian industry is spending just 0.2% of the GDP on research. So this is the research money spent by the industry within the industry. This is not the money that is even coming to the institutions or anything. And the world average, for example, US industry spend 2.7% of GDP on the industry research. South Korea is among the fastest, among the most well-known country in that respect. I was looking at some data. the South Korean industries during a certain period have spent something like their increase in R&D expenditure in the industry has gone up by something like 1,000 times, right? That is what made Samsungs and LGs what they are today. Indian industry, the model is you get technologies from somewhere, you manufacture them, you slightly modify things here and there, and then make money out of it. I think most of the Indian industries are built on the imported technologies, nothing that has actually come out of India which has made these industries as big as what they are. There may be some exceptions here and there. India is a large country, so whatever you say, even the opposite is also true. So therefore, I don't want to generalize too many things, but the general trend is that, a lot of these are not homegrown technologies, our industry is actually built upon. So this is one challenge that we have. How do we make Indian industry to actually spend money on R&D and collaborate with academia and then build a new age industries, the new age technologies, new products? I think that is where India needs to put its act together. And that is also happening primarily because academia industry collaborations in India are pretty bad. Hardly any noteworthy collaboration between academia and industry, except for here and there, nothing much has happened. Even in terms of rankings, we rank something like 66th among 130 countries when it comes to academia industry collaboration. So I believe unless these things change, I don't think anything much will happen. Even ISM, setting up some foundries, manufacturing some chips out of some imported technologies is not going to change anything for the country. We will still remain what we are. And I think that is where, Professor Rao and Professor Tumala Rao, the kind of initiatives that he has put together, he has brought in all these institutions, but he has also brought in equal number of industries. I think that is one thing which many of us have not been very successful in doing. I think if at all we can do that, all these academic institutions collaborating with all the industries that he has listed out in his slide, I think we will be on a firmer ground at least this time. But if it doesn't happen, I think it will be some low-level manufacturing happening in the country. I don't think that will really change anything for the country. So that's one thing which is what it is. This semiconductor research journey for India actually started way back in 2006. That is when IIT Bombay and IISc Bangalore, some of us together put together a proposal, and that proposal at that time was the single largest proposal ever funded by Government of India. That was 100 crores. That was the money that was allocated to us. And subsequently, many IITs joined hands, IIT Delhi, IIT Kharagpur, IIT Madras, IIT Guwahati, all these institutions became part of it. Now there are excellent facilities available in at least 7 institutions in the country, with state-of-the-art kind of fabrication lines. And this is how it all started. The CEN, the Centers of Excellence in Nanoelectronics, this is where the journey began. And then there was INUP, which is the Indian Nanoelectronics Users Program. The idea was to build a user base. Just 2 institutions doing nanoelectronics research, we thought will not change anything. India is a large country. So we started an Indian Nanoelectronics Users Program where anybody from the country can come and use these facilities and get trained. So that was how the 2008, the nanoelectronics program started. Then the phase 2 began, and then other institutions joined hands. The cumulative investment into these 7 institutions today stands at 700 crores. That's a total amount of money we have been able to get from MeitY, the Ministry of Electronics, as well as the DST to the tune of 700 crores. In dollars, it's roughly $80 million to $100 million. The exchange rates keep changing, but when we started the project, it was all like $100 million kind of an investment, which has gone into setting up these facilities in these 7 institutions. There are other institutions which have also, so this is what we call the NETRA, the N-NETRA kind of a scheme, and this is where the 7 institutions currently stand. And with a cumulative investment of 700 crores since 2006, right? So it's almost like, the 18 years, the 700 crores is the investment that has gone into. And this is a national resource that we have. And then subsequently, in BITS Pilani also we have set up a center of excellence now. with funding from our alumni and with some funding coming from Government of India. And in fact, Prime Minister of the country, Mr. Narendra Modi, he visited IISc Bangalore a few years ago. And even Biden visited IIT Bombay. So while IIT Bombay have leading facilities in this area, so we had all of these high-profile visits at that time. And we also have state-of-the-art infrastructure. So most of these are nano fabrication facilities. There are excellent characterization facilities. There are roll-to-roll kind of printing. IIT Kanpur has pioneered that roll-to-roll kind of printing technologies. There are some packaging facilities, but India doesn't have enough expertise in packaging. While we have good expertise in fabrication of devices, packaging India has long way to go. Thanks to Professor Tumala Rao, hopefully that is one thing that will pick up right now. And because packaging is not happening, the system integration also hasn't happened so much. While a lot of devices got fabricated, and many papers got published, the putting the full system together, I think India has been lagging behind. That is also an effort in this phase, which Professor Rao is driving. And the equipment design, in fact, as part of this initiative, equipment design also took place. A few technology transfers happened in that space. And so in terms of the impact, the human resources, India has done pretty well in this respect. You would see that there are about 607 institutions, which have produced manpower. And in terms of people who can go to a foundry, right, a fab lab, and then make some MOS capacitors or even make some devices, that number would be about 8,000 people. That's what these facilities produce. These people know clean rooms. They can go there, do oxidation, etching, all of these processes, and finally make a device. So that number over the last 16 years, we produced about 8,000 kind of people, and a lot of publications came out of this. And then, so this is where it stands right now. Many of these facilities are being used by anywhere from 2,000 to 3,000 people. That's a total count of students who are actually going to fab labs in India and actually fabricating something with their own hands. That number stands at 2,000 to 3,000 people, thanks to these 7 facilities which have been established in various institutions in the country. The industry usage is also picking up now. As you can see, in the last few years, 4,000 to 5,000 people are beginning to come to these foundries, use it in the service model. They pay some money to use these facilities. So this is where we currently stand right now in terms of the usage. And there are also certificate programs. At IIT Bombay, for example, we started one with the applied materials. There is a certificate program for semiconductor manufacturing. And a similar certificate program we started in BITS Pilani. After I moved to BITS Pilani, after spending 25 years in IIT Bombay and IIT Delhi, we are building these semiconductor activities in BITS Pilani in a major way. There is a very interesting course offered, in fact, coordinated by Professor Tumala Rao, with involvement of 6 or 7 institutions from all over the world and industries on the packaging. So this is also one course that has definitely become very popular now in the country. Every time the 3rd edition is starting now, every, I think, batch of students or every batch of participants, there are at least 200 to 300 people who are using these, who are making use of this course that is currently on offer. And in terms of impact on science and technology, one thing that has definitely happened is India's rank in terms of publications in top journals and venues. If you look at the IEEE electron device letters, IEEE electron device letters, or IEEE transactions and electron devices, India ranks 2nd or 3rd. In fact, we figure only after Europe, only after US or China, and then comes India. So we are in the top 5 countries when it comes to publications in IEEE transactions on electron devices, IEEE electron device letters. So this is one thing that has also taken place. This is a study done by my colleagues from IIT Bombay. They put together the publications in EDL and TED. So all this has started to happen thanks to these facilities. And today, if you look at any of these high-tech areas, whether sensors or quantum or nano or bio, right? In terms of research output, India is among the top 5 countries. In terms of the research papers published in top venues, India is among the top 5 countries. So a lot of good research is happening. But I think the next goal is how do we take this research forward and translate that knowledge into something which is a product or which is a prototype, collaborate with industry so that the industry can make use of this knowledge that is coming out of academia. So that part is definitely missing right now. But in terms of academic research, Indian researchers are indeed doing pretty well at the world scale. And even in terms of prototypes and TOTs, thanks to this $100 million funding that has gone into in the last 18 years, you also see many products in the market. For example, these are all the technology readiness levels at different levels. The TRL-9, these products are currently available in the market. In Delhi airport, if you go, Bombay airport, if you go, you see explosive detectors which have actually come out of these centers. In fact, these have come out of a company which I incubated at IIT Bombay, NanoSniff. So many, at least a dozen airports in India use the MEMS-based explosive detectors, and that is thanks to these facilities, some of that has happened. The last column are the products which are currently available in the market. The pressure sensors are actually have gone into the Indian space. The satellites are actually using some of these pressure sensors developed at IISc Bangalore, and a few other things I have listed out there. So that's a good beginning. These are all the startups that have come out of this initiative. So all these 7 institutions, if you look at startups which have become successful and with products in the market, so I've just listed out some of these startups now. So I think this is what the investment has done now in the last 18 years. In terms of publications, we have done pretty well. We reached top 5 in the world in terms of electron devices. In terms of innovation, the full system development, we have made a good beginning, but we still have a long way to go in terms of churning out technologies which industry can use or getting products into the market which have a global visibility. I think these 2 things have definitely can be better. But we have definitely made a beginning, and we definitely have the strengths right now in the country thanks to all the investments that have happened. But the biggest challenge currently is the bridge the broken bridge between academia and industry. So while academia is doing very well on its own, the industry is getting all these imported technologies and making some businesses. But I think academia-industry collaboration is what is missing, and that is where I would think Professor Tumala Rao needs to act as the bridge. So he is the one who needs to build that bridge between academia and industry, which has unfortunately so far not happened in the country. So I think this is where I would stop. And the systems focus, of course, is something that is very critical, very important. To me, the India semiconductor mission needs to look like this, right? So while you have all these fabs that are coming up, the biggest thing that everybody is talking of is a $10 billion investment government of India is making. These advanced CMOS fabs are happening. There are also other kind of fabs that need to come up. But what to me is very important is at least $1 billion investment going into academia. I think that to me will be a game changer. If that doesn't happen, I think it will be another run-of-the-mill kind of a project which wouldn't yield anything much as far as innovation potential in the country is required. Whereas if you look at US, I was talking with Mukesh Kare, my classmate from IIT Bombay, who is now vice president in IBM. What he says is in the US CHIPS Act, right? The $10 billion have actually gone to academia. No industry in the US has received any money from the CHIPS program of US. What they have actually done is they have first started funding academia, and now they are funding the industry. Whereas in India, industries have received quite a bit of money, but academic projects haven't been funded so far. The centers that Professor Rao is talking about, I think that is something that we need to do better, and I hope that will happen as part of the ISM program. So I'll stop here. This is what I believe that needs to happen into the commercial fabs, right? The manpower, the research centers, the technology, the startups. I think that research center part is very critical for us to make good use of the 10 billion investment that Government of India is making into ISM. Thank you very much.
we have a short panel discussion with the directors of IITs that are still here. So please come on over here. Professor Satya, Professor Murthy, sir. Huh? Okay. That's fine. That's fine. Okay. Let me see who else. I thought we have a few more. We have Dean. Oh, okay. All right. Yeah. Come on, sir. So I have only one simple question now. Okay, I'll repeat when everybody comes. Okay. He went out. Should we wait for him? Okay, he's here. Where is he? Come on, sir. Yeah. Okay, so what you heard all afternoon, at least from me, okay, so we're really depending on the transformation of Indian institutes, the academic institute, the way they work with industry, or the way they receive the money from the government. So we're talking about major changes. So, sir, my question is going to be the following. You have done a fantastic job producing the very best students. They're everywhere, including US. Half of my students came from India. They became the very best. So you're producing the very best students here. Okay, and but the way you operate for today, same thing goes throughout the world. You have faculty, you have students. Okay, you have limited labs. You don't have the state-of-the-art labs for most part, except what Professor Ram Gopal talked about at IIT Bombay and the Indian Institute of Science. Okay, in some selective areas. Okay, so tomorrow, basically, we want to transform India, as you heard from me. The transformation requires these, okay, the institutes to be entirely different from what they are today. Okay, of course they have the faculty are the masterminds. Students, okay, without students we're nothing. Okay, but to be able to develop technologies that are useful to companies to grow the economy of India, okay, it requires people like full-time research faculty with expertise from industry, not postdocs. Postdocs come and go. They come here to learn and go on to get a better job. So full-time research faculty, pilot lines to integrate a lot of things. Remember, we're after integration. Pilot lines to be able to do that. Okay, on top of that, we want industry engineers. The problem is, as you know, in the US at least, so we do fantastic research at the universities. Corporations never count on that research being useful to them. Therefore, they do totally on their own. Then we end up doing twice, one at the universities, one at the companies. So to solve that problem, the model that I developed at Georgia Tech involves industry engineers on campus in every project. So in fact, in my industry consortium, I tell companies, okay, that they are interested. Sir, we'll take you only. You can be a member only if you can place an engineer on campus. Okay, American companies typically don't like to do that because they think they can do much better job at the company. So, but we've been very successful, without which I'll guarantee you will not have been as successful, in fact, will not have been successful. So the model sort of requires, therefore, the new model, we call industry core development model, requires state-of-the-art infrastructure, research faculty, academic faculty, of course, the students, of course, okay, on top of the industry engineers on campus, okay, and they all work together, not only explore technologies, integrate towards what I call D&D, design and demonstrate prototypes for industry. So, are you willing to do that to make India successful? And what is that you're going to do to make it successful? One question to each of you.
Hello. Okay. No. So I can only tell what we are doing. So, as you have rightly pointed out, and I have also realized over 3 decades of my experience that we want to do something that results in a commercially viable product right from beginning. The research activity should be always jointly with an industry. So this is a very important thing, but it doesn't get satisfied easily. But now we see that happening in the area of silicon carbide. So we have actually started with a 45 crore project on silicon carbide crystal growth, jointly with an academic institution, jointly with an industry. So that is what I want to say. I think that is very important for any successful commercial product in the area of semiconductors.
Please go ahead,
sir.
Professor Murthy from IIT Hyderabad.
I'm from IIT Hyderabad, sir. 3 things I want to say. First and foremost, you see India is changing. The fact that you see a lot of industry people sitting together with us is a clear example that things are changing. And I see, in institutions like us ourselves, whether it is academia. I remember on May 1st, 2022, I met you for the first time. You talked that in Georgia Tech, you could not start a master's program on packaging. In 3 months, on August 1st, our classes started on masters in packaging. So India is moving fast, I can tell you. We have a BTech program on semiconductors, which now AICTE has taken up, and 125 engineering colleges, a BTech program on semiconductors, which is called IC Design and Technology, has been started. So academics, India is now talking about generating the required quantity of engineers when the fabs are going to come. So on the academics, definitely there is a lot of progress happening. The second is industry connect. There is, I would say, at least again taking IIT Hyderabad example, we have 50% of our master's projects are industry defined problems at IIT Hyderabad. So this is something, is something that you...
Who defines the faculty?
So the way we do is, we have something called a 1 credit course called industry lectures, which is mandatory for all master's students. We have 35 master's programs. In every program we have this course. And then industry comes, gives lecture for 1 hour, and then we ask them, can you list up a list of problems which our master students can do 1 full year? They can go and sit in an industry for full year and do that project.
Yeah.
So this is something that
I'm going to challenge you here.
Sure.
Okay. Almost every university, every professor works with companies. That's what they do. That's what they tell me they do. So that's what I call passive partnership with companies in India. And same thing goes in the US as well. So in other words, a company has some money, they're interested in students, they give a project, but my point is they don't count on that technology being useful to them into
Exactly.
products. We need to correct that problem.
Exactly.
Okay?
So these are getting converted into technologies, and you will see it very soon that happening.
Yeah.
Third point I want to tell you, research. Okay, when you talk of semiconductors, you need a lot of characterization. At IIT Hyderabad, we have now set up a 80 crore facility called In situ and Correlative Microscopy Center. For example, a microscope called an atom probe. Okay, there are only 5 pieces of this in the whole world. Samsung has bought 4 of them. This is called 6000 series LEAP. And Japan has one. IIT Hyderabad has the 6th piece of the world sitting already installed, and people started working on it. So now I would like to see all these people. For example, IISc Bangalore talked about advanced materials. We should be able to put every one of them into microscopes like that to see whatever you are doping, where is it going and sitting. So unless you do that, real high-end technologies at small scale will not happen. So that's another area that we should think of. And finally, training people, hands-on training. Many of our friends talking about. We have initiated that with Purdue and NTHU very recently, and we have now a proposal ready to train 1,000 students a year. in the area.
Sir, let me
So we are all working on that.
Let me be more specific. Right now, you are proposing, let me say, 1.5 centers at IIT Hyderabad. One is, okay, photonics, okay, you call it co-packaged optics. The other is, okay, assembly and packaging for photonic devices. By Shiv, okay, for example. So that's very different from what you've been doing. You have COEs, now we're talking about industry core development centers. In your opinion, what do you think you can do or you want to do to make them successful? We now have a lot of companies. We saw nothing but companies all day today, this afternoon. From everybody, I had 5, 10, 20 companies ready to work with you. So before they lose interest, we got to make sure, okay, they are treated as a customer, okay, and therefore you listen to, define a problem, solve the problem, and give that information to the company as a customer. Okay, it's not a passive; it's very active. You're an active partner,
This
customer. It's more than a partner; it's a customer actually. So, are you willing to do that?
Already, sir, this is happening. I would say Suzuki Global R&D Center is at IIT Hyderabad now.
Yeah.
So things are happening.
Yeah.
I'm sure every one of my friends also have similar examples to quote. So I think the vision of yours, the dream of yours is happening, and I'm sure in the next 5 years we will be able to demonstrate this.
Thank you. Professor Ram Gopal, basically you identified the single biggest problem. He said the following in my view. We are capable of doing the very best research in the world, but that research we're not able to connect with the industry. So what ideas do you have to solve that problem?
If you ask me the 3 fundamental problems with Indian research, I mean, there are exceptions, like I said. I think I don't want to generalize everything, but one thing is subcritical funding for research. India never funds any project, to the fullest extent possible. Everything is bits and pieces, and connecting those bits and pieces is often a pretty challenging task. I think if you want to achieve something, that subcritical funding aspect needs to be taken care of. Even the centers that you are proposing, I think they need to be generously funded, and that's one thing which is very critical. The second thing, as I have also mentioned, is the lack of academia-industry collaboration. I think these two entities not working with each other, and even the industry also not doing enough research on its own. I think even that culture in the industry is grossly missing, as you can see from the percentage of GDP money they are spending on their own research. I think that's a cultural problem with Indian industries, but I think Indian industries are mostly in the service kind of areas, so probably it hasn't happened. Now if we want to get into manufacturing, I think that has to happen. But even in automotive sector, right, where India is a huge powerhouse of manufacturing, even in pharmacy, I don't think we are spending enough on R&D. Right? Therefore, not much innovation has happened even in the automotive sector, where India is exporting to 150 countries, but these are all components kind of a thing, right? Even in pharmaceuticals, there is not a single drug developed from India which has got FDA approval. So, though we are the powerhouse of manufacturing in pharmacy or even in automotive, the innovation part is still missing. I think that is something that research investments need to happen even within the industries. The third thing is the lack of system focus. I think in academia, though we are publishing lots of papers, but the system focus is grossly again inadequate. As a result, complete products or complete systems haven't come out of academia, which are what are required in terms of making an impact. So I think this to me are the basic kind of challenges. In fact, there is a very nice World Bank report about the middle income trap kind of a thing. I think the 3 I's which are very important for any nation to progress is for importing technology, which is good, nothing wrong in that. So China has also imported lots of technologies. To import, the next one is infusion of technologies, that culture of manufacturing. So you import and then you build that culture of building things. The third thing is the innovation. I think when innovation doesn't happen, if you only stop with the importing and infusion of that technology without much innovation, I don't think you will survive for too long. I think India needs to focus on innovation now, along with the import and infusion. The innovation needs to happen. Otherwise, I think another automotive industry
what difference will it make? I mean, of course, it is producing jobs now, but there are still, the job-wise, India needs to produce almost like, a million jobs per month now for the next few years. To look into our median age, as Secretary said, is around 28 years. I think, there are so many people looking for a job now. Some of these things need to happen at some point. So to me, subcritical funding of research, lack of academia-industry collaboration, lack of system focus. These are the three things that we need to very consciously work if we want to ever improve upon things. I think there are multiple schemes and all that one can think of.
Thank you. Thank
So
you. Thank
I
you
want
very
to
much.
add, relate to capacity building, we have focus on skill and research, but not as much focus on entrepreneurship. So if we want again, commercialization of ideas, when people are being introduced to research, simultaneously they must be exposed to entrepreneurship. So in fact, at IIT Bhubaneswar, we have a course called Introduction to Research and Entrepreneurship for all research scholars. They undergo this course so that right from beginning, they can think how they can translate their ideas into commercial products, and also how they can choose ideas which are amenable for conversion in commercial products. So this is one point I want to make.
Thank you. Thank you.
Just want to add something.
Yeah.
I just want to add on what Professor is saying. We have started an MTech in techno-entrepreneurship. At the end of the 2 years, the student will have a product in hand and a business model. So this is an area which we have to focus a lot.
Thank you. So Professor Satya, so you're proposing a center on system level electrical test. Very different from what you're used to because of all the things that are needed. The most important being treating industry folks that are here, treating them as customers to deliver to. Partnership, is not, that word is not strong enough in my view. You really have to think of it as a customer, and they got to be involved in the project. Otherwise, they won't count on that project being useful to them. So what are some of the things you're going to do to make your center successful?
So thank you, Professor Rao Tumla. First of all, I would like to really thank you for taking this initiative. Now, a couple of points I wanted to make was one, the point that Professor Ram Gopal Rao has been talking about the industry not spending enough on research. In around 2017, once I started going to IIT Tirupati to set up IIT Tirupati, near our institute we have the big industrial park, Sri City, where a 10,000-acre private industrial park where there were 170 plus companies, many Japanese companies. So I said we will set up, to work closely with the industry there, we'll set up an industry institute center there. And I called the Dean of Sponsored Research and Consulting from IIT Madras, because we were new. IIT Tirupati still did not have enough wherewithal to do this. And visited about 7-8 companies to just understand the ecosystem there. And said we will physically locate a center there so that there's a strong interaction between the industry and the academia. But to our surprise, we found that none of them were interested in any development, because they said many of them are there are companies that are set up with American or French, Italian, Japanese background, and any even small problem, we found even a problem that needed about 1 lakh rupee to address was referred to the headquarters, right? And so we found that there was really not much interest in really setting up such a center, because these are looked at only as manufacturing hands rather than doing anything development thus. So that was a lesson learned for us, that we need to really have a much stronger interaction. Now, one of the other issues is how do we create the strong interaction? One of the things I think we also need to do from our academia side is to get our faculty to go spend time in the industry. Every summer or during the year, spend 1 or 2 months closely with them. We need to incentivize it. We need to incentivize them to go do this, which I don't think we do adequately, because at the end of the day, their promotion is based only mainly on the papers they publish, and so they don't see this as incentive to do it. So these are some of the things that we need to start creating frameworks where we get faculty also to work closely with the industry and the industry also come to this. Recently, we had Chris Gopalakrishnan, one of the founders of Infosys in our campus, and he was talking about this, that the industry needs to engage much more closely with the academia. So he says TCS has taken a decision that a lot of their research will happen in the academic institutions, and they'll start co-locating their research people from the industry in the academia. Now, I think this is a great move. If that starts happening, this will enable lot more strong correlations. Of course, the research parks that have come up, starting from the IIT Madras Research Park and the ones in Bombay and other places, these are also creating opportunities for co-locating the industry people coming closer to this. Now, this is something that I think all of us should leverage, and I think the great idea that, nice idea that Rao Tumla Garu has been talking about in the ICC, that the industry needs to come and put their engineers there. They need to work very closely with this. So these are all things that are required, and now all of us are also started in professors of practice, where we are bringing in people from the industry to give that connect between the industry and the academia. And this is a scheme that is catching on, and all of us are expanding on. Recently, for example, we have got Mr. Muralidharan, the Chief Technology Officer of Tata Advanced Systems, to come as a professor of practice with us. And he's talking about starting a course on systems engineering. How do you design to manufacturing? How do you bring in the whole systems together? So these are the kinds of things that we need to, and I think all of us are looking at anywhere from 10 to 20% of our faculty members being professors of practice. So, so we need a stronger engagement between the industry, between the industry and the academia. And one more thing is, how do we call it the value of death, as we've been talking about. TRL 1, 2, 3 is what we academia work towards, and then the industry is looking from 6 to 8 or 9 to take it to manufacturing. What happens between 3 and 6? Now we need to, and that's what they're calling value of death, and we need to get our faculty members also to work closely with the industry to take it to at least 6, where there's this interface that's happening. So these are all things that we need to do, and I think there's a lot of awareness now, and a lot of things are happening, and I would like to really thank you for stitching together, bringing so many of the people from across the IITs and the other institutions on a common platform and creating these teams. I don't think it's happened at this scale so far, and hats off to you for enabling this. Thank you very much.
Thank you. Okay, sorry, you wanted to talk a little bit? Okay, let me ask you a question. So you are from IIT Kanpur, right? So you have center here, headed by Nilesh. Where are you? Okay, that's extremely, for most people, packaging means assembly. That's what he's doing, next generation of assembly. But he wants to go not only IC assembly, board assembly, and on and on and on. He's got lots of companies. He's got more companies than perhaps any other one for sure. So therefore, okay, what can you do to make sure the customers who's paying, who are members of the center, are totally satisfied, and therefore you keep on growing industry academic programs?
Thank you, Professor Tumla. My name is Jayendran Rao. I am representing Professor Manindra Agrawal, who unfortunately is in Bombay for a National Quantum Mission meeting. First of all, I think I would like to thank you for perpetuating this vision to the next generation of researchers, including Professor Nilesh Badwe, who is going to lead the Industry Core Development Center on IC assembly as well as testing. In terms of our facilitation, both to the faculty member as well as to the industry partners, I would imagine the requirements to start with would be physical infrastructure and space. We are committed to giving the space that Professor Badwe needs to set up this initiative, very important initiative. The second component that I see is he would also, as well as the industry partners who come on board, would definitely need access to experts as well as critical infrastructure available in the institute. This would span probably the Center for Flexible Electronics, the Center for Cybersecurity. We are also setting up the Center for Quantum Mission right now. And all of this expertise would be available with respect to the professor working in the institute as well as the industry partners. And I also recognize that the industry engineers would be quite pivotal for the success of this initiative. We'll be happy to provide them the housing, the necessary infrastructure that is needed to conduct their research, and also to provide the academic ambience so that their work prospers in this. The bigger issue or the vision that we probably are looking at here is we are probably going to play catch-up for the next 5 to 7 years, but the vision that you have perpetuated is to stay ahead of the curve for decades to come. And whatever it takes to be successful in this, we would be happy to provide to faculty members and industry collaborators.
Oh, thank you. Thank you very much. We need to stop here because of time limitations. As a token of gift, we'd like to give you this massive proposal. We're giving it to very few people. We would like you to read and come back next time. Okay, sir, we are ready for the next session.
Thank you so much. We understand that we might be a little delayed, but would like to request all of you to please take your seats. Everyone, please take your seats, as I would like to do the honor to invite Mr. Virappa. Ladies and gentlemen, would like to request all of you to please take your seat. All right, so please put your hands together as I welcome the chairman of TSOLVE. Please put your hands together for Mr. Virappa, ladies and gentlemen.
I think we'll take it over from here. They're all kind of anxious to go home. Yeah, I'll take care of it. Okay, so we had last session, this industry panel, industry session. Okay, and so as I've been saying, this whole program is based on industry, okay, co-development with industry, co-development with industry, not development with academics. We're working together to develop the technologies. Okay, a lot of companies, about 70 of them are interested, and about 30 of them, I don't know if you have a slide, either slide, Nilesh, that shows a list of all the companies. Next one? Okay, can you go to the next one? I'll take 1 minute. Next slide. Okay, these are the companies. There are about 70 companies that expressed interest in joining our program. So far, those highlighted in yellow, they're committed, okay, in terms of investing so far. Okay, so what we're going to do now with your help, okay, so those companies that committed to that, they filled one slide. These are the areas we're interested. We're interested in research, workforce, and on and on and on. So now I'm going to turn it over to you. Okay, so there's one slide. When he calls for when he calls the name of the company, that person responsible, okay, for that company as a representative, please come up, okay, and speak for a minute. So, can we go to the next slide?
Good evening. We are late by only 52 minutes. Okay, so I think you all know, right, the background of whole thing. Professor Rao has been working on this. He always tells that, most of you are not born when he started working. So that's what he tells, like 55 years plus everything. So he has gone through the entire cycle of packaging and, Georgia Tech. So this is to make it very short that there are about 20 companies who are going to be in the thing today. So I'll share that each one got this right. The time allowed is 1.5 minutes. Professor said 1 minute. I said by the time you come up and go down itself, the time is get over. So 1.5 minutes. It's the last session. We don't want to hold you beyond. Like we will try to finish it not 1 hour. We'll finish it much earlier than 1 hour. We will try to save some time. I'll start with. I think he's not there. Vinashana is not there from Infineon. Go to the next slide. Keynes. Raghu is there or who's coming for the Keynes? Sharath call from. Up, come here. Keynes, the next slide. Keynes, you have. No, next slide. Right. Sharath, no, start.
Check, hello. Yeah, Keynes SEMICON, you would have seen the announcement. We got approval from the ISM last week, and we're expecting the government order soon. And we have 4. Okay, thank you. Thank you, sir. Thank you. So we're very excited about collaborating with the IDSPS. We've chosen 4 SRAs. Number 1 is the photonics with IIT Hyderabad. The second is the thermal with IIT Kharagpur.
Next slide, yeah. This is Infineon. He has to go to Keynes. You have to, right.
The third would be the organic and glass substrates with IIT Bombay. And of course, the predictive modeling with IIT Gandhinagar. With IIT Hyderabad, we have an MOU already, and we have collaboration with 2 US companies, Mixtech Technologies as well as Lightspeed Photonics. Then on to the engineer on campus. Probably we'll switch that now that I've heard from Professor Rao how eloquently he explained the importance of having an engineer on campus. To be frank, we really didn't think it through. But now with your clarification of how important that actually is, we'll reconsider that and we can change that to a yes, most likely. Okay. But definitely eminent faculty were on board as well as 2 PhD scholars. And definitely we're going to be interested in the workforce development as well as the R&D, not just either or. Yeah, that's it.
Thank you. On time. Who's SFO? SFO, okay, sir. You're a partner now. This is a memento.
Good evening. I am Samuel from SFO Technologies. We are a photonics and electronics design and manufacturing company. We are interested in the co-packaged optics, also the integrated sensors and MEMS, and also on the power electronics area. We are committed on the engineer on campus, the PhD scholars, and also will be a would like to become a full-time member. Thank you.
Thank you. This is really quick. Thanks. Next is Arun. Arun from Intel. Arun, where are you? Come.
So you're a partner in the proposal.
Okay. Good evening. I represent Intel. Rather than read through some of this, of course, as Professor Rao said, we are really interested in everything, right? This is the first phase, and we'll eventually engage over the years into everything. But I would rather take a minute and talk about what value we want to bring to this. So if you remember Professor Rao's slides, there are 4 aspects: design, research, technology development, and manufacturing. Intel has already been in India in design for the last 2.5 decades. This allows us to put a foot into research and contribute. Manufacturing and technology development will eventually come, but I can say with a lot of pride that Intel is one company where we can, under the same roof, contribute to all those 4 pillars. Thank you.
Next is McDermott Alpha, Ravi Bhatkal. Okay, you are representing. Come. Ravi is not there. Morgan. Nirgana Rebus from.
Good afternoon, everyone. So most of you have seen me in the meetings together with Ravi Bhatkal. And unfortunately, he could not be here today. And I think I will have to borrow the words of the previous presenter that we are interested in everything, right? We have been supporting this team for more than 2 years now, attending meetings, and we are very interested in collaborating across all the IITs and IISc. We have already been supporting several of these institutions, and we are looking forward to more and more opportunities that we will come from this. And I assured Professor Rao just before, because I could not attend the whole day, that we are fully committed to this. Thank you.
Thank you. Next is Corning, Indranil Chakraborty. There? Anybody from Corning? I think we will skip next. ANSYS, Anil Kumar from ANSYS. Huh? Abhimanyu from ANSYS, okay. ANSYS. Next.
Good afternoon. Good afternoon, everyone. This is Abhimanyu. I am representing ANSYS, and I'm filling in for Sheetal Joshi, who couldn't be here. He had to travel back. So we play a unique role here. If you see, as a technology enabler, we develop and market engineering simulation software, which is used across engineering discipline. Now, there is one predictive modeling SRA where we are closely integrated and working closely with Professor Tarun Agarwal. But then we see a greater role that we can play across various SRAs. Some of the SRAs we have shown interest other than predictive modeling is co-packaged optics, 6G integrated systems, IC board, power electronics, and thermal management, where we are continuously interacting with the group leads, co-leads, but we see a greater role that ANSYS can play, and we have been invested continuously attending meetings for the last couple of years. And thank you, Professor Rao, for guiding us throughout. So thank you, Professor Rao Tumala. We are happy to be here.
AMD, Raja, I don't see Raja here from AMD. Anybody from AMD? Okay, next is Resanok Kudo Hedge, right? Good to see you.
Hello, my name is Abe from Resonac, Executive Director. So Resonac is like a former Hitachi Chemical, so we are a global #1 packaging materials company. Also, we do some front-end materials. But we are more nowadays focusing on advanced packaging. We are running pilot line in Japan, and also we will start advanced packaging pilot line in US as well. And then we will running some consortium style in both Japan and US to accelerate the development of test vehicle for ecosystem. So hopefully we want to be involved more in this India activity. And then of course we are very interested in material to work with. Thank you very much.
Thank you. Next is Andy McKee from Indium Corporation. Anybody from Indium? I don't think they're here. Next is Mr. Naveen Vishnai, Executive Committee member, Board member of ISA, Country Manager of Marvel. I know him well.
Thank you. So from Marvel, since we are a fabless design company, our focus has been mostly on the design and extending into the test. So that's where we are committed. We have been working with the Professor Rao and Jay and other team to put up these electrical test SRA team, and we'll continue to build on it. But also the logic architecture is also a key area of interest for us to keep building on it. We already have a proposal as part of the electrical test. We are looking for an academia partner to build on that. Nikhil from our team is leading that, and we are committed to the overall program and the intent here. Thank you.
Paresh, I didn't know Paresh from Teradyne. Oh, yeah, you're here. Come. You're on time, Paresh. Paresh is all the way traveled from the US.
So I represent Teradyne. People who don't know, all the semiconductor companies, they need us. Pretty much most of the semiconductor testing is done either on our platform or on our competitors. The area what we are interested in is specifically the system level test. All the other areas are very important to us. Please make a lot of progress there. That's when all the system level test is going to be useful. We're also interested in the co-package optics, and that's because the challenges of co-package optics testing are a lot different than the system level testing. That's all. All the best.
Thank you. Thank you, Paresh. Krishna Thakur from L&T Semiconductor. Krishna is here. Are anybody from L&T? I don't see Krishna. I don't see Krishna. Nobody from L&T. Lam Research, anyone is here? Analog Devices, Srinivas Prasad. I think they all left for the day. Applied Materials, Mayur.
So, as most of you know, Applied Materials has the broadest portfolio of semiconductor equipment, starting from deposition, etching, all the way to inspection and metrology. So, we'd like to partner with this effort for the areas of interconnection, interconnecting substrates, predictive modeling, co-package optics, materials, device, and packaging. This will help us, be prepared for the new materials research, how our equipment can be ready for incorporating the latest technology. So we are looking forward to this exciting engagement. Thank you.
Thank you. Pradeep from Micron. Anyone from Micron? Pradeep, welcome. Gokul from Micron.
Hi. Okay. So yeah, I'm Gokul. I'm the senior director for Micron Packaging. So we have been very involved with this effort for the last 1 year or more. Just like Arun said, Micron also has all the way from early design, IP, R&D into manufacturing. So we are deeply engaged and committed to India, and also with this R&D program. We believe that we are interested in everything, but just to make sure we deliver the focus, we are working closely with Professor Nilesh and IIT Kanpur, because we think system level reliability is going to be fundamental in many things. And we have CL Gunn, who's the leader for reliability from Micron, closely collaborating. So we continue to increase, and hopefully we'll see more of this as we continue to evolve. Thank you.
Thank you, thank you. Rakesh Gupta from Baba Fine Chemicals.
Hello, my name is Rakesh Gupta. I'm from Baba Fine Chemical. I'm actually a material engineer and a supplier from USA before the miniaturization started. And I'm so glad to see this initiative in India. I planted Baba Fine Chemical seed in India in 1997. So far, 100% of my sales are export. And I'm hoping some will be domestic coming soon. I'm really looking forward to that. And the major research I'm looking into is I'm working with Professor Deepak Arora on low K dielectric materials in Jodhpur. And also I have been working with Professor Satinder Kumar from IIT Mandi. And then also with the Professor Nilesh Badwe on the IC board assembly. Actually, there is a new innovation in conductive inks, and we are India exclusive supplier in that materials, and we're going to look into the next generation metallization techniques in this industry. Thank you very much.
Thank you. Next, Preet Yadav from NXP Semiconductor. NXP, anybody is there? Preet Yadav.
Good to see you.
Ram Trichur from Henkel. Ram Trichur. Henkel, I don't think. I think that's... No, nobody. the list is done. I think Professor Rao has put 13 slides.
How come you're not there on the list? Yeah, TI.
Hey, I'm Stalin from Texas Instruments. So we discussed how we will engage with the activities happening here, and so the way we have decided internally is we have a large pool of technical leaders inside, and what we thought is instead of pulling Spocks from the US, for example, who work mainly on device physics materials, we wanted to get people in India, work with the universities here, and accordingly some of the areas we will not be able to get people right away, which is mostly material science, device physics, but anything which is to do with circuit design, let's say very high speed, ADCs, 6G, all of those we have interest, and we will collaborate. And that's the way we thought we'll sustain it through.
I think pretty much. Sterling. Ashish Budani from Sterling.
Good evening. My name is Ashish Bhutani from Sterling, India. We deal with liquid nitrogen oxygen plants, and we are having a pioneer in this segment from last close to 70 years. Our first production started way back in 1955 with PLN model, and now we do have fourth generation machine, which is most rugged. And semiconductor industry, the biggest enemy is vacuum, and we are very good into doing that with the help of cryogenics. Thank you so much.
Any company? Anyone else?
Absolutely. Yeah, once you go.
Sanjay Mohe from RFIC Solution.
Please go ahead.
So this is a very good effort. Our company, RFIC Solutions, does design RF radio frequency chips, and we have been doing it for the last 15 years in India and USA. And all these efforts in packaging and circuit design, modeling, all these areas we are interested. So it's a very good effort. Thank you, Dr. Rao. It's an excellent team you have put together. And all the IITs that are contributing in this is great. Thank you.
I think pretty much anyone, we are done. So I just want to tell.
Anybody else? Anybody from companies? So those of you from companies, raise your hand. From companies that have not received the book.
Venki, you want to speak? Venki wanted to come.
Oh yeah.
Yes.
No.
You don't want to say.
No, I can say. You've done. Huh? See.
Oh, no, yeah, it's fine. I just wanted to say I expect no? No. Leave it, it's fine.
Right.
Okay, so now we have some copies. So let's decide. Maybe our faculty leads. Okay. Again, companies, anybody wants a proposal because you're interested in the technology, you want to be part of this, the program we described. Raghu, how about you? Why don't I give you a copy? Your own copy, Raghu. Congratulations. Congratulations again.
Thanks a lot.
Oh, thank you.
Thank you for all the support.
Oh,
Sharing all the process.
yes, sir.
We all know that. Thank you.
Thank you. Sir, you also have something? You want a proposal? From where are you from? Huh?
Baba Fine.
Oh, yeah.
Thank you.
Who are you from? Well, oh.
I'll get in touch with you. We have a lot of.
Okay. Anybody else? Okay. Yeah. Yes,
Freeze from NXT. Sorry,
Oh, you-
I have to step down for
you-
another meeting because it was running a little late.
Yeah.
I think almost you have come to the end, and I can to the.
With that, thank you so much, ladies and gentlemen, for joining in here. With that, we come to the conclusion of the workshop. Thank you so much. Wish you all a great day ahead. If you have any queries, sir is here. You can always connect to the person one by one. Thank you so much.